Валерий Николаевич, здрасте. У вас микрофон выключен. У вас в зуме выключен микрофон, Валерий Николаевич. Слышно меня? Похоже, мы друг друга не слышим.
Так, вот вы сейчас слышите меня?
Вот, сейчас стало слышно.
Я вас слышу хорошо.
Отлично. Смотрите, демонстрация экрана – это такая штука. Вы открываете ваш файл на своем компьютере. Наверное, Acrobat Reader запустится или аналогичная программа. А потом в Zoom внизу есть такая зеленая кнопка демонстрации экрана. Вот если вы видите.
Ну, у меня компьютер, то есть этот файл, он где-то в стороне, так сказать. Как я его добуду? Вот я...
В каком смысле в стороне? Вы Zoom запустили на компьютере, да?
Где-то я боюсь, что вот это...
Я могу вам обратно по e-mail послать ваши слайды.
Я посылал файл, да.
Я говорю, если он у вас потерялся, я могу обратно их вам послать.
Нет, он у меня не потерялся, я не знаю, как его туда вставить.
А его не надо ставить, надо его просто открыть, как обычно, независимо от Zoom. Его надо просто открыть, ткнуть на него в файловом менеджере.
Алло, день добрый. Валерий Николаевич.
Файл не надо нести в Zoom, надо его открыть, как будто бы Zoom вообще не было, а потом в Zoom ткнуть внизу кнопочку демонстрации экрана и выбрать это окно. Там будут варианты.
Валерий Николаевич, как будто для себя откройте слайды на своем компьютере. Как будто проверяете просто.
Если что, у вас выключен микрофон сейчас, поэтому если вы что-то говорите, мы вас не слышим.
У вас выключена камера и микрофон. Ну, без камеры мы обойдемся, но без микрофона тяжело.
Ну, может, так и задумано.
Может и нет.
Видимо, с двух устройств. Хорошо, Валерий Николаевич, тогда надо очень аккуратно с микрофонами, чтобы там не возникало.
К сожалению, мало времени у меня было. Вот я не освоил эту технику.
Но там есть зеленая кнопка демонстрация экрана.
Надо сначала на том устройстве, на котором лежит файл со слайдами, открыть этот файл, как будто сам его хочет читать на своем экране. Вот он открылся, не трогать его, но окно побольше.
Но при этом я как бы выхожу из сайта конференции. Вот,
Нет, ну она же, это же ваша, наверное, Windows многооконная система. В одном окне будет сайт конференции. И вот это окошко надо как-нибудь просто уменьшить, например, чтобы осталось место. А потом совершенно независимо от этого открывается файл и обратно в это окно конференции, войдя, нажать кнопку демонстрации экрана. И все, что для себя открыто, будет показываться нам.
Нет.
Если этой кнопки не видно, просто мышкой поводите внизу экрана, она появится.
Или, может быть, она, если экран узкий, то она может быть под троеточием, там, где дополнительно то, что не влезло в ширину экрана.
В худшем случае мы можем сами демонстрировать.
Ну, в принципе, да, можем открыть тут файл. Но лучше бы, потому что придется все время командовать следующую страницу, предыдущую страницу. Можем, конечно. Кстати, PDF-то здесь чем открывается? Акробатом. Сейчас, файл у нас просто прицеплен к программе. Прицеплен, я помню. Его из браузера надо открыть. В браузере открылся. Какие еще можно сделать?
Можно скачать.
Скачиваем. Кладем в ту папочку. Открываем браузер. Так. Что?
Браузер, сам файл менеджер.
Желтенький, да. Синий кто такой интересный? Синий это email, я понял. Так, он был на рабочем столе. Он был в слайдах. В принципе, открыли. Если что. Ну, наверное, борется с интерфейсом.
У него до сих пор не вышел звук.
У него вообще вылетел.
Он вылетел.
Ну, один раз сумел подсоединиться, значит и дальше присоединиться. Тем более у нее там два устройства.
Мы вас не слышим. Включите микрофон.
Я говорю, не получается.
Ну, только если совсем не получится, можем у себя демонстрировать. А где это окно? Вот окно, все, нашел окно. Сколько времени-то? 8 минут есть. Валерий Николаевич, получилось открыть файл? А теперь вернуться в окно зума и внизу искать зеленую кнопочку демонстрации экрана. Если ее нажать, вот у нас там, где у нас проектор выводит на стену, вот появляется окошко такое, и там можно выбрать, какой файл, какой из открытых ваших окон хотите демонстрировать.
Все уже не показываешь, да?
Не надо.
Не надо?
Я думаю.
Боюсь, что я говорю еще и совсем сейчас не соображаю после бессонной ночи.
Давайте тогда мы откроем у себя и будем здесь демонстрировать.
Угу.
Так, мы уже у себя открыли. Так, демонстрация экрана. Тогда вам придется командовать, что нам нужно, мы должны листать.
Можно так, чтобы я видел, или я сам должен...
Сейчас будет.
Да, вот я очень хорошо вижу. Вы меня слышите?
Да.
Да, вот
Давайте там Ctrl. Так, что-то у меня... Я то открыл.
Нет, ну это заголовок, первая страница.
Вот такое. Видно?
Да. И я должен буду вам говорить, что следующий, да?
Ну да, командуйте следующий слайд. Там next и так далее.
Давайте так вот, несколько
У нас-
такой.
Помотать? Ну, я никого не нашел, могу.
Ну вот я буду читать тогда так. Я хорошо вижу текст. А буду командовать следующий и так далее. Да,
Вот второй слайд.
Да. Я очень хорошо вижу.
Ну, прекрасно, тогда давайте так и будем
Ну
делать.
хорошо, еще рано, значит, 5 минут где-то, да?
5 минут еще есть. Да, кнопку нажимать это полезная функция. Это я не очень уверенно делаю. Я ГН попросил, но ГН плохая связь. Придется мне утром проверять.
У вас с кнопками тоже проблема, да?
Ну, конечно, голова-то не резиновая.
У нас вот эта сигнализация в доме уже лет 30 стоит. Я до сих пор не могу ее пользоваться. Обязательно не ту кнопку.
Я не знаю, может быть, мое изображение моей головы не нужно.
Но оно сбоку маленьком окошке. Оно не мешает. Я так понимаю, что каждый сам настраивает у себя, видно ему, сколько ему участников видно. Можно только одного, можно сколько влезет.
Ну, тогда будете командовать, когда начало, я, значит, начну.
Вам нужно не абстракция.
Не абстрактно, ну, я открыл на телефоне.
Там какой-то еще щит есть. Где что-то влез. В принципе, главное, все не налаживается.
Это чтобы было меня слышно, да? Надо сюда. So, let us start today's morning session. The first speaker today is Valery Berestovsky from Novosibirsk Sobolev Institute, and His title is Solution to a Generalization of One Toponogov's Problem. Ray Nikolaevich?
Okay. So there was the title of my talk. First of all, I'm very obliged to organizer to invite me to this conference. So please give next file. So in this, of course, you heard about the main result of Toponogov, his theorem about comparison of triangle. I will speak about some simple problem. Beside it, a very deep idea was, okay, in the early 1970s, Viktor Andreevich proposed the following interesting problem. This was problem for students, not for scientists. So let at the closed upper half plane of the Cartesian plane xy, there is defined a continuously differentiable real valued function f such that fx0 identically equal at 0 and partial derivative of f with respect to y by modulus less or equal the partial derivative of x of f by x by modulus everywhere. Proves that f is equal to 0 elsewhere. It's interesting that, at least for me, it is unknown whether somebody beside me solved this problem. I heard about this problem occasionally 12 years ago in some conference in Omsk University. I heard this from Rafael Sarkisyan. He proved somewhere in Moscow, I don't know exactly. So the first positive solution of this problem was obtained. This is my paper. I will show you at the end. As a corollary of the following result. So this is theorem 1. Let f be a continuously differentiable real valued function on a closed half space. I will not read exactly all formulas. It would be too tedious. Such that, so this is half space, positive half space, such that the partial derivative of f by t by modulus is less or equal a multiple by norm of such vector, constitute of partial derivative by another derivative, where a is non-negative constant, and this is usual standard Euclidean norm on this space. Then for each point in this half space, there exists a point in this intersection, I will show you a little later, such that the value of function f in the initial point is equal of value of f in another point, where this point line in this intersection. This is simply hyperplane where the last coordinates is equal to 0. And this is really some cone, intersection of some cone, this cone with half space. C is such cone. Is pointed closed cone. Okay, last file, please. In the notation of condition of theorem 1, it is equivalent to the following theorem 2. If for each point in the above half space, there exists a non-zero vector v from that cone such that the differential of this function at the point u calculated with respect to vector v is equal to 0, then for each point in this half space, there is a point in the above intersection such that fu1 is equal fu0. And note that theorem 1 and 2 are trivial if a is equal to 0. If a is positive, we shall give a somewhat different interpretation of theorem 2 and its natural generalization. To do this, we shall recall a necessary definition from book. I will show you this book. Okay, next page. So at first in definition 1, I repeat, not the usual definition of Lorentz manifolds. This is a pair Mg, where M is C infinity smooth manifold of dimension n plus 1, which is equal or which is more or equal to 2, and G is small symmetric tensor field of type 0, 2. This tensor is called Lorentzian trichonomy with the signature, the following signature: plus dots, plus minus. Then a vector, then a non-zero vector in tangent bundle of M is called non-space-like. So we give a definition or a different definition in one and the same place. Non-space-like, respectively time-like, isotropic, space-like, if we have the corresponding inequality or equality. Okay, non-space-like, it means that this is less or equal 0. Time-like, which means that this is strongly less than 0. Isotropic, when this equal to 0, and space-like if we have this strong inequality. I think many of you know this definition. And then another definition too. If a Lorentzian manifold Mg admits a global, smooth, time-like vector field, this means that every value of this vector field is time-like in this sense. Then the manifold Mg is called time-oriented by the field X. Then we can give another definitions. Then any non-spaceless vector tangent to M at the point P is either future-directed or past-directed, which means that if I have this inequality, which means this future-directed, or this inequality, which means past-directed. Okay, next one. And now, using the previous definition, we defined a very important notion. Of course, at first we defined the causal feature, G plus Y, of L, where L is arbitrary set point, or respectively the causal past. What this means? If you consider corresponding subset in Lorentzian manifold, is defined this one first. As a set of all point Q of M, for which there exists a continuous, piecewise continuously differentiable curve, with future-directed or respectively past-directed non-space-like tangent vector, such that the initial point of this curve belongs to L, and the last point of this curve is equal to Q. So in some sense, let's give some visual interpretation of this curve. In some sense, we have the notion of light, speed of light is in some sense can depends on vector. So this curve, in some sense, in every point cannot be more than speed of light, but it can be equal to speed of light. And this every tangent vector must be future directed or past directed in some sense. And we shall call shortly curve of both such type as non-space-like curves. So in some sense, this means maybe you know, if you consider the usual Minkowski space, then there is a notion of speed of light in this Minkowski space times. So if we cannot speak with more speed than speed of light, then we have this causal feature if we direct it in future. Or if you going in the past, then we have the causal past according with this. So we cannot move more than speed of light. But if we always the tangent vector has speed strongly less of speed of light, then we have the corresponding notion of chronological future and chronological past. So one more, this is speed light is strongly less than speed of tangent vector strongly less than speed of light. Then we can, if you have this for notion, then we can give another definition for a space-time. What is a space-time? I give exact definition. It is a connected Hausdorff C-infinity smooth Lorentzian manifold with countable base of the topology tau and a time orientation x, field x. A space-time is called globally hyperbolic if there are satisfied two conditions. Is it possible to move above? So the first condition that the intersection of chronological future and chronological past of some point which may be different constitute a base of topology tau. This is the first condition. And the second condition means that intersection of causal future with respect to some point P and causal past for some points are always compact subset. Okay, please give next page. It's interesting that the condition one of this definition means that the topology tau coincides with so-called interval topology of Alexander Danilovich Alexandrov. Base topology composed of this intersection of chronological future and chronological past. A space-time with this property is said to be strongly causal with respect to this book, which I give you references later. The simplest example of a globally hyperbolic space-time is a Minkowski space-time. It is usual manifold with such dimension, Lorentzian metric having constant component of this form. They are equal to 0 if indices I and J different, and this component if they coincide. The time orientation determined by the vector field x with the constant component of this form in canonical coordinate of such space. Then it's clear that for positive A, theorem 2 is equivalent to the following. Theorem 3 of the same paper. So if you consider the same half space of the Minkowski space-time now, then we state that for each point in the half space there exists non-zero non-space-like vector such that the differential, I don't know whether this is visual or not place for you?
Yes, we can see it.
If the differential of the corresponding function f is equal to 0 at the point u with respect to vector v, then the statement that for any point in this half space there is a point u0, I can state now in the causal path of this point u, such that the value of this function are equal. Unfortunately, I cannot give you illustration. It would be quite clear what this means. So one more, if we have this definition for differential of this function, then for any point in the half space, there is a preceding point in the sense of causal path, which have the same value like point u1. Okay, please give the next page. Okay, definition 5 from the same book, a knot space like cow, I defined this previously, is said to be inextendable if there are no limits. If you go to this from the right to A, or if you go to B from the left, there is no limit. And then we give definition 6, a Cauchy surface in the space-time Mg of dimension n+1 is a closed subset as in this space-time that is n-dimensional topological manifold intersected with any inextendable non-space like cow in Mg at exactly one point. Exactly one point, if you consider this cow. If S is any Cauchy surface in the space-time Mg, then you have this inequality with respect to this Cauchy surface. Okay, please give next. Okay, there is a theorem for, really this is a famous theorem by Richard Gerach. A space-time is globally hyperbolic in previous sense if and only if it admits a Cauchy surface. And another theorem by the same Gerach, for any Cauchy surface in a globally hyperbolic space-time Mg, there exists a homeomorphism of this form, such that a preimage of such sets for any T in R is a Cauchy surface. There was a long-standing question if we can take in any globally hyperbolic space-time smooth Cauchy surface. And then appeared relatively recently the following theorem 6. I will give you references. So that any globally hyperbolic space-time admits a smooth Cauchy surface as such that corresponding homeomorphism is in fact diffeomorphism. Okay, please give next page. Then we have the following theorem. Really, it generalizes the corresponding statement which I gave you previously for Minkowski space-time. So I will not repeat this correlate, which really I stated previously. So what if you have any globally hyperbolic space-time with a Cauchy surface S, and F any continuously differentiable real valued function, Then for each point, there exists a non-zero non-space-like vector V in such tangent space such that differential of this function at point u with respect to v is equal 0. This is condition. Then for each point in the causal future of this Cauchy surface, respectively for any points in the causal past for this Cauchy surface, there exists a point in this Cauchy surface, and with respect to causal past in the first case, respectively in intersection of this Cauchy surface in causal past of the point u1, such that values at these 2 points are coincide. Really, because Minkowski is globally hyperbolic, then the previous statement follows from this theorem. So that's the most general theorem which I proved in my papers concerning this question of Toponokov. Okay, please give the next page. So now I consider some example. Next example is a very interesting example, so-called de Sitter spacetime of the first kind. So really, like I said, this is simply one-sheeted hyperboloid of this form. R a fixed positive number, and this is hyperboloid considered in the Minkowski spacetime, which I considered previously. And we simply take the Lorentz metric in Minkowski spacetime and induce it on this hyperboloid. And the result we have exactly de Sitter spacetime of the first kind. And here the time orientation defined by the tangent vector field y to this orthogonal to all space-like section of the form of such form. When the last component of this point is constant. And the last component of this vector field y is equal to 1. The above sets, these sets, then all this above, please excuse me, all these sets are exactly Cauchy surfaces. And the isometric group of Minkowski and de Sitter spacetime act transitively on the set of time-like geodesics and on each such geodesic. Okay, please, let's give. So I can give much more visual interpretation corresponding condition of this function f. Really, we have the following proposition 1, which proved in the next, second my paper. And continuously differential real function f of Lorentz Emmanuel has property as in previous theorem 3 and 7. I simply repeat this previous condition. And what is important, if and only if f has non-time-like gradient. It seems much more simple condition, non-time-like gradient. If you remember what this non-time-like vector, then at every point this function has non-time-like gradient. Really, I don't know other mathematician beside me who consider function with this property. But there are many papers which consider a function with opposite property. I mean, smooth function with time-like gradient. And really, this condition is very important. And we give you corresponding example of application of this function. Please give next page. Suppose that we have Lorentzian manifolds and there exists a smooth real-valued function with time-lag gradient. It is clear then that this Lorentzian manifold is a space-time. Really, this gradient supplied the time orientation in the sense of previous definition. And then, with respect to this gradient, considered like time orientation, this function will be strictly increasing along every continuous, piecewise continuous and differentiable future directed curve. It is in terms of the same book, the function, this function will be global time function. So in all point of this manifold, we have function, we have some time, value of some time in some sense. Space-time admits a continuous global time function if and only if it's stably causal. I will not explain what this means. This notion is given in this book. And what is important, every stably causal space-time is Lorentz causal. I remind you this is the first condition in definition of globally hyperbolic space-times. And then we prove the following theorem 8 in the second my paper. Really, this paper was written with my future formal student, Irina Zubareva. A connected Lorentzian manifold admitting a smooth function with time-lag gradient is globally hyperbolic if all level sets are compact. To prove this theorem, we prove that for every value t, the value set is a Cauchy surface and imply theorem 4, previous theorem 4. Please give next page. So there is, in some sense, not problem, but maybe conjecture. What if we omit the condition that this level set are compact and consider more general condition? So there arose a question: is it true that a Lorentzian manifold admitting smooth function with time-lag gradient is globally hyperbolic if all level sets of this function are complete Riemannian manifolds and there exists constant, positive constant K1, K2, such that we have this inequality? So what this is conjecture in some sense, so I don't know whether it is true or not. It would be interesting if it would be true. Please give next page, please. So let's consider some interval which may be infinite also, and consider some smooth positive function. This definition is very known for geometers. So let's consider at first M0, G0 smooth Riemannian manifolds. Then we can define the smooth Lorentzian manifold, which is like manifolds direct product of this Riemannian as this interval. And we define the Lorentzian metric in the following, by the following formula. Please multiply this Riemannian metric by this function, and then take the direct sum with this form. And this is called var product and denoted in this notation. Then we have the following example, 1 from this book 5. Then this function which define like a composition of this function sigma and P2, where P2 is a projection onto the second factor, will be a smooth function on this Lorentzian manifolds with Stalin-Malak gradient, which satisfies this equality. At this, there is the following theorem from that book 5, a space-time of this form, var product, is globally hyperbolic if and only if the remaining manifold is geodesically complete. And here, all the non-empty level set of this function of the same form like previous ST are Cauchy surfaces of this work product. Okay, please go next page. And another famous example of globally hyperbolic Lorentzian manifolds. So we can consider any Friedmann cosmological model. They are especially for dimensional space-times which possible singularities satisfying the Einstein equations. So all these cosmological models admit a smooth global time function with time-like gradient. Here, this set may be different from R, and every level set is isometric to a space of constant non-zero curvature of constant side or a point, and at this point exactly singularity of this model. Moreover, this function, which is curvature corresponding section, is identically equal k, where k is constant, or another possibility, every kinetic component of this model, if we remove all singularity of this point, is a Ware product with smooth Cauchy surfaces. ST, so the letter is globally hyperbolic by theorem. So one more, if we consider Friedmann cosmological model with non-constant curvature, then we get and remove all singularity, then we have Ware product, so we will have global hyperbolic space-time by theorem 9. Friedmann calls his cosmological model with constant kT stationary. In his work of this year, Friedmann observed that Einstein cylindrical model and the de Sitter spacetime, which I mentioned previously, of the field kind, are particular cases of his stationary model with k more than 0. Okay, if you consider the Ware product, but this remaining manifold would be Riemannian symmetric space of rank 1. What in other words, what this means? In other words, at a point homogeneous space. What this means? 2 points. For any 2 points, there is isometry of this Riemannian manifold, which move. If this point, if we have two pair of points which equal distance, then any 2 pairs can be isometrically mapped from one to another one. So if this one more, is a Riemannian symmetric space of rank 1, then we have so-called Robertson-Walker space-time. In view of the theorem 9, they are globally hyperbolic and have smooth Cauchy surfaces ST of previous form. Friedmann cosmological model, which are Ware product, are particular cases of Robertson-Walker spacetime. Note that the cosmological models which satisfy the so-called cosmological principle, one more I will not give you exact definition here, are necessary Robertson-Walker spacetimes. Okay, let's go further. So now, okay, oh, maybe I missed, please give previous page. Oh, no, excuse me. Okay, I finished the main part of my talk. So this was my first problem where I gave the solution of problem of Toponogov, and here I prove theorem 1 and 2. And there was statement that really the corresponding result is true for global hyperbolic spacetime, but really I only state in this first paper. In this statement about global hyperbolic spacetime, we proved in this paper with my future student Zubareва. And there we consider function of two sorts, with non-time-like gradient, which I mentioned previously, and also with time-like gradient. Here considered another question which I did not mention in my talk. Really, this, if you consider time-like geodesics, L, and consider the causal future or causal past of this geodesic, then the boundary of this usually known as event horizon. And we consider event horizon particularly in for space de Sitter space-time of the first kind. It's clear. It's interesting that in famous book I'm sorry, there was some mistake. Maybe I mention later. And this is particular cases, my recent paper, Lorentzian manifold closer to the Euclidean space. There I consider especially de Sitter spacetime, Einstein spacetime, and this is main source of definition in my talk. It's Beam. It's interesting that Beam was a former student of another known geometer, Herbert Busemann, and this is his colleague. This other appeared in the second edition only. The first one was only to these others. And we take all main definition from this book 5. Okay, next page, please give. This is a paper of Gerich, which I mentioned, where he introduced the notion of surface, or Cauchy surface, and prove the corresponding characterization of globally hyperbolic spacetime in terms of Cauchy surfaces. And this is paper 7, where it was proved that we can take smooth Cauchy hypersurfaces in every smooth globally hyperbolic spacetime. And this is selected, this is book in Russian, selected book by Friedman, which was printed in this year. Maybe I will mention that famous physician Gamov was really a former student of Friedman. Gamov, maybe you know Gamov, which connected is the conjecture with Big Bang. It was first pronounced by Gamov. Maybe because of Friedman constructed cosmological model with singularity. Really, like singularity, maybe a Big Bang, exactly Big Bang, which you know this. And this is Weinberg, which I statement the correspondent. Please return previous pages. Was this cosmological principle? Please below. Please go next page. So this cosmological, or maybe next one. I'm sorry. Next one. What cosmological principle, which is stated in this book by Steven Weinberg. Maybe you know that Steven Weinberg, together with Glashow, gave Nobel Prize in physics. So this connected with this particular notion which I mentioned in my talk. By some reason, I did not sleep this time. It was connected with my flight from America to Novosibirsk. It was delay of flights, etc. So I appeared in Russia after a short, only the short time. The previous two was unsuccessful. Please excuse me. I think that my talk was not the best form. So I finished my talk. Thank you for attention. So maybe the last page. The very last page in my, this one. Thank you very much. Excuse me.
So, thank you. Are there any questions from Zoom? Please don't forget to unmute your microphones before asking questions. Okay, any questions from the room? Oops. Oh, well, I have one. I enjoyed your problem too, which was about this functions with time-like gradients, right?
Yeah.
Valery Nikolaevich, do you hear me? Do you know anything about what happens if you replace the complete assumption by being closed, I mean, with respect to ambient topology, not compact, but just closed? Are there any counterexamples?
No, really, I was a specialist in this. All this was real corollary of my interest in Toponogov problem. So I don't know answer on your question. I think that your question also very interesting. One more, I give that in special case, when we consider var product Lorentzian manifolds, then necessary and sufficient condition that this would be globally hyperbolic, the corresponding M0 must be complete. So we also consider this complete Riemannian manifolds must be.
Yeah, thanks. Other questions from Zoom or from the room? If there are none, let's thank the speaker again.
Thank you.
And we have a break for 11 minutes. Yeah. And then next talk is 5 to 11, right? Yeah.
Could I use the time to just check if everything works with my system? And the next speaker.
Probably.
Hello. We can't hear you very clearly. Can you probably put your microphone closer to your mouth or do something?
The microphone is not good.
We don't hear you enough.
Okay,
Well, I mean, your
fine.
voice.
That's the reason I asked.
Yeah, that's better. That's better at the moment.
Everything is ready. I know the microphone. Okay. Can you hear me now? Not good. Is it better now? Can you hear me now more clearly?
You what?
Can you hear me now better than before?
Yes, that's
Yeah,
this.
I think it seems to be better, right? I try another one. I couldn't try this before. I'm sorry for this. So let me switch with this one.
Oh, by the way, I have a question
Is this better? No, this is
about
Yes?
your presentation. Is it the same style of file if with small letters? I have print out to hand out to people here if you like.
Well, I can share if you allow me. Oh, sorry.
Yeah, everyone.
I share my screen so you can
You
see
just can share, and yeah, let.
how it looks. Let me see. Can you hear me now? No.
Yes.
Probably not. Yeah, it's good. Okay, so let's stay with this microphone. Is this okay like this? Can you hear
Yes.
me? Good.
Yes,
Okay.
it's okay too.
Good. Then I stay with this. Now I try to share my screen. Let me see. I need. Yeah. This is here. Okay. Screen. Okay. I try to share my screen. Select application. Probably this one. Okay, so now I cannot see the screen anymore. Is it okay for you?
Yeah, it's readable. It's
readable. It's clearly readable from the distance.
Well, I have printed it on paper. If you didn't change it,
Yeah,
so
no,
I can.
I change it.
Oh,
I
you
was
change it.
constantly changing it.
It's not.
Is it better like this? Could you just?
Yeah, it's better
look
to
at
be a
it?
little bit larger.
Yeah. Okay. So I make it as large as I can.
This is okay, yeah.
This is okay. Yes, on the wall.
Yeah. Okay. So I stay with it.
Надо вот эту правую убрать
Good.
куда-нибудь.
Do I have to talk loudly? I mean, or is it okay, the noise?
This is okay.
Okay, very good. So
So
thank you
it's-
for.
It's
then
5
I
minutes.
guess I'm done with my test. So Yeah. Okay, maybe I come back to the other version without.
Так, телефон.
Ah, oh, I made a mistake. Okay. Can you hear me like this? Okay.
Here, it's less loud than it used to be, but it's okay. У нас микрофон включен? Наш. But your slide has stopped being shared. Something. We do no longer see your text on the screen. So
I will do this a little bit later. I will show it a little bit later.
it's intentional. I see. Okay,
That's intentional.
I saw
I
the.
hope I come back.
So we have to already. So almost time now. So let's continue our session. The next speaker this morning is Joost Heinrich Eschenburg from University of Augsburg, and his his title is From Milner's Morse Theory to the Thom Isomorphism. So please.
Yeah, thank you. Good morning, ladies and gentlemen. It's my great pleasure to give a talk on this conference in honor of Viktor Tobolnogov, and I thank the organizers for inviting me to this event. In fact, I was influenced a lot by the work of Professor Tobolnogov, in particular by his famous triangle comparison theorem. This was a starting point for global Riemannian geometry, in particular in connection to non-negative sectional curvature. The sphere theorem of Berger and Klingenberg and the Soul theorem of Giger, Gromol, and Meyer are just two of its many strong applications. And since Klingenberg and Meyer were two of my teachers, I can consider myself as a grandson or great-grandson of Professor Tobolnogov. I'm proud. The most prominent examples of this domain of Riemannian geometry, non-negative curvature, the most prominent examples are the indecomposable compact symmetric spaces, of course. These are spaces which are interesting not only as individual spaces, but also, and this is my message today, as the whole family. As was pointed out in John Milner's extremely beautiful book on Morse theory, written by Spivak and Wells, these spaces together as an ensemble, at least a good deal of them, contribute to homotopy theory. They occur.
Sorry, just in case we don't see any slides.
No, not yet. In a moment, please have a little bit of patience. At least a good deal of them contribute to homotopy theory of these symmetric spaces. They occur as iterated centrioles, sort of equators, for the classical complex Lie groups, which leads at the end to Bott periodicity theorem. In recent work, together with Bernhard Heinke from Augsburg, we extend Milner's approach in two ways, giving new proofs of the result of Atiyah, Bott, and Shapiro, old paper 64, who used the results of Milner but did not use the methods of Milner. We do. The first is we give normal forms for all maps from the sphere into a classical group up to homotopy. Considering those maps as clutching maps for vector bundles over n spheres, these are turned into generalized Hopf bundles. And second, when n is a multiple of 4, Milner's method allows, dependent on arbitrary many, but boundedly many, additional local parameters. Thus, we may replace the n-sphere by certain n-sphere bundles over finite CW complexes. This leads to a geometric view of the Thom isomorphism theorem in K-theory. So now let me start with my slides. I hope I can share. Can you see this?
Yes?
Yeah, very good. So let me start with Milner's construction, which is in his book on Morse theory of 63, I think it was first published. We need the notion of poles and equators and meridians which are notions from the sphere. So if you have a round sphere, Sk sitting in Rk plus 1 Euclidean space, then the North Pole and the South Pole are just plus minus E sub k plus 1. And we have meridians, shortest geodesics, great circles from N to S. And we have the equator, call it S1. The equator is the set of midpoints of the meridians. Okay, so this structure can be handed over to many compact symmetric spaces. Call it P, the compact symmetric space. What is a symmetric space? We have a symmetry at each point P of this space, capital P. A symmetry is a point reflection. It fixes the point P and reflects all the geodesic through P. And it's an isometry of order 2, of course. Now, what is a pole? If we have two different points, O and P in P, in capital P, then the point P is called a pole of O if and only if the symmetries at P and of O agree. In other words, P is an isolated fixed point of SO. For instance, if you look at the sphere again, we have the North Pole and the South Pole, and the symmetry at the North Pole is just a reflection of this axis between North and South Pole. So it's the same as the symmetry at the South Pole. But this happens for many symmetric spaces. Now, if we have poles in a symmetric space, we also have meridians. These are shortest geodesics from O to P. Look at the right part of this picture here. We have P and we have the two poles, O and P, and the meridians shortest geodesics. The meridians in S will be called mu, and the meridians in P will be called gamma. And again, there is the midpoint set of all these meridians. The points situated precisely in the middle between O and P on these meridians. But different from the sphere, in general, this midpoint set need not to be connected. It can have several connected components. And the connected components will be called centrioles, with connected components of the midpoint sets of meridians, fixed O and P, of course. Now, these meridians are connected components of fixed point sets of isometries, of involutions, in fact, like the equator, which is the fixed point set of the reflection at the equator. And so the same happens for these equators in an arbitrary symmetric space at the centrioles. So the centrioles are reflective submanifold, as one calls it, fixed point sets, so connected component of fixed sets of involutions, and as such, they are totally geodesic. Remember that a short geodesic in the ambient space is uniquely determined by its endpoints. So if the endpoints are in P1, in this subset, if it would be outside P1, then you would have a second one, namely by reflection. So we have one upstairs, one downstairs, two geodesics connecting the 2 points, which is impossible, so it must lie inside P1. So reflective submanifolds are totally geodesic. They contain all the geodesic connections, at least the short ones, inside the ambient space. And totally geodesic in a symmetric space implies symmetric again, so P1 is another symmetric space. Now, the main message and the main construction of Milnor is the following observation. By an index condition, which I'm explaining below, any map phi from capital S to P, sending poles to poles, or better, this is no real condition, sending one of the meridians, call it mu0, sorry, into one of the meridians of P, gamma 0, just one. So this is the assumption for phi. So in particular, of course, N must be mapped to O and S is mapped to P. So if we have such a map, then we can deform it under this index condition, which I did not yet explain, into another map phi tilde, still from S to P, but now mapping all meridians onto all meridians of S onto meridians of P. And therefore, also the midpoints of the meridians in S are mapped to the midpoints of the meridians in P. So, of course, in a component, because everything is connected, so it's mapped into a centriole. So the restriction of this map phi tilde, this deformed map, is a restriction to S1, to the equator, is just a map from S1 to P1. Now, how do I make this deformation? Well, you can see it roughly from this picture. The phi maps any mu into a curve from P to O. Any curve can be ugly, not a geodesic. And now we take all these curves together from O to P, the images of the meridians, and we shorten them together. I will explain this how it works. And then they become geodesics. Now, this deformation is relative in the sense that if we have already one of these short curves, if one of these curves is already a geodesic, like gamma 0, for instance, then it does not change under this deformation anymore. So in this way, maps from S to P can be compared to maps from S1 to P1. More precisely, the maps from S1 to P1, star means that the base points are preserved. Maps from S1 to P1 embed into maps from SP as follows. If we have now any map from S1 to P1, we can extend it to a map from S to P as follows. If we have any point in S, say this one here, it lies on a mu, on some meridian. The meridian is mapped to another meridian, gamma. Sorry, it has a base point in S1, of course, here. So the base point is mapped to a base point in P1. And now we look at the gamma, which is determined by this base point. And we put this point to this point here in the same position, affine position on gamma as it was before on mu. So this is what we call a geodesic suspension. So we get from a map from S1 to P1 by geodesic suspension from O and P, we get a map from S to P. And this is uniquely determined. And so we have an inclusion of the map of S1 to P1 into the map of S to P. And this inclusion turns out to be homotopy equivalence up to dimension d, some dimension d, which is related to this index condition. And the inverse, so to speak, is we take a map phi from S to P, we deform it into phi tilde, and then we map it to phi 1, which is just the restriction of phi tilde to S1. So because this is a homotopy equivalence in low dimensions, in particular, the homotopy groups of P and P1 are the same, but up to this index shift. Here we have S, here we have S1. And we can iterate this. We can, instead of P, we can take P1, and we can take a centriole of P1, and more general, we can take a centriole of Pj and call it Pj plus 1. So we can iterate the centriole notion, centriole, 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 and so on. And then, of course, by the same arguments, we have Pk of P, the same of Pk minus 1, P1, Pk minus 2, P2, and so on, Pk minus I, Pi. For instance, if P is the SOP, the orthogonal, special orthogonal group in P dimensions, then P8 of this space, the eighth iterated centriole, we will compute this in a moment, is just SOP over 16. So it's again an SOP. So if you let the dimension P go to infinity, then we get Pk of SO infinity is Pk minus 8 of SO infinity. And this is Bott periodicity theorem. Now I have to explain you two things. I have to work out a little bit on this notion of centrioles. Why do we have centrioles in many symmetric spaces? And I have to explain you how this deformation process, how this simultaneous shortening works. So this is the next slide, centrioles and Clifford families. So what is, in particular, we are concentrating on SOP. We could do the same with the unitary group or the symplectic group, but they are all a little bit different. Let's stay with SOP. So what are the iterated centrioles of SOP? So first of all, P is even. It's assumed to be even. At the end, it's very, very big. So we can assume it to be even. So in particular, minus identity is inside SOP, and identity and minus identity is a pair of poles, of course. And a shortest geodesic, a meridian between identity and minus identity, is first of all a one-parameter group, or part of a one-parameter group, because it runs through identity. Geodesic in a compact Lie group with bi-invariant metric running through identity is one parameter group. And so we can see what the midpoints are. The midpoints is it's parameterized on the unit interval. So the midpoint is gamma of 1/2. So a gamma of 1/2 squared is gamma of 1, which is minus identity. So J squared is minus identity. In other words, J is a complex structure, this midpoint. So therefore, P1 is the set of complex structures in SOP and a connected component of this. In fact, there are two connected components of complex structures in SOP. And we take a base point J1. We fix a base point. Now, let me iterate this. A chain of iterated centrioles is related, is connected to a set of anti-commuting complex structures, J1 up to JR. Anti-commuting Ji, Jj is minus Jj, Ji. This is also called a Clifford family. set of anti-commuting complex structures. And the pi plus 1, the next centriole, is just the set of all j of pi such that j anti-commutes with all its predecessors with j1 up to ji. And we take a connected component of the set, and inside we take a base point ji plus 1. So we see how this chain of iterated centrioles is connected to Clifford triangles. And now it's easy to compute the first period by the periodicity theorem. We only need the first period. So we have pk. K runs from 0 to 8 in some sense, because k plus 4 is in the next line. So we start with SO8Q. So the first is a set of complex structures, SO8Q over U4Q. The next is we have two complex structures anti-commuting. So it's a quaternionic structure, U4Q over SP2Q. And next, if we have three complex structures, their product gives an involution again. And so an involution has two eigenspaces, plus and minus one eigenspace. So we get an element of a Grassmannian inside H2Q, because everything is compatible with the quaternionic structure, which we got before. Of course, we can have any dimension here, but if we want to continue this, we need half dimension. And the next step is those Q planes in H2Q, which are graphs of asymmetries. So this is SPQ again, symplectic group in Q quaternionic dimensions. And then we can continue with SPQ. We can again have SPQ over UQ. And then, well, this is one complex structure. Here we have two complex structures, which gives a quaternionic structure, but everything is an SPQ. So they commute with a given quaternionic structure. Two quaternionic structures which commute give a real structure. And so UQ over OQ is the next step. And then we get the real Grassmannian, and we end up with the orthogonal group again. And so you see the periodicity. We start with an orthogonal group, we end up with an orthogonal group. Now, the fundamental groups of these are Z2, 0, Z, Z, 0, 0, 0, 0, Z, Z2, Z2. So the only place where we have infinite fundamental group is here, where K is 2 mod 4, and we will need this later. Now let me come to the index condition. And this is where Morse theory comes into the business. But instead, you will see that in some sense, Milnor is not really using Morse theory, but avoiding Morse theory. I will explain this. So the space on which Morse theory will take place is a space of paths in P from O to P, from between these poles, as before. Any path, well, because we need the energy function, we have to assume it's H1, but instead we also can assume already that omega is a broken geodesic with a bounded number of breakpoints, in fact. So we come back to a finite dimensional manifold again. This is a Milnor trick already. So we have a manifold of these paths from O to P, and we have a function on it, the energy function, the integral over omega prime derivative squared, which is more or less the same as the distance of the length function. And of course, the minimum set of E omega min is a set of shortest geodesics between O and P. And now the idea is you'll use the flow of the minus the gradient of E, flow of minus gradient E, to move any point omega right down into omega minus. And for most points, omega, small omega, this works. But there are some exceptions. You can see them on this line here. The exceptions lie on the domain of influence, of dependence of the non-minimal critical points, of the non-minimal geodesics. I will call them gamma tilde all the way. Then, if you have a point here, it will flow down this line and will stay here at gamma tilde and will not go to the minimum. But if this domain of influence delta plus is small, that means has large codimension, it's easy to avoid it. Any point can avoid it anyway, but we will have more bigger objects which also should avoid them. So what is the dimension? No, sorry, what is the codimension of delta plus? This is the dimension of delta minus, which is obviously just a domain of influence for the gradient of gamma tilde. And the dimension of delta plus is just the index of the Hessian of the energy function at this point. That means the index in Morse theory. So if this index of gamma tilde is big, then delta plus has big codimension, is small, and can be avoided. So this is why I said Milnor tries to avoid Morse theory instead of applying it. So why is this index large? This is now the main question. Now I cannot explain you this in detail in all these examples, but I can show you a model case, namely, that's very easy, the sphere itself, SP, where P is very big. Now what is a non-minimal geodesic between N and S? Now it cannot go directly from N to S, but it needs to be a great circle, of course, or inside the great circle. So it must run from N to S, over S, to N back, and then to S, or several times the same round. So let's stay with this easiest case. It runs from N to S, then to N, and then to S again, 1.5 times around the great circle. Then we have 2 points, S and N, where we can shorten this geodesic. All these parts have the same length, so this is really smaller because we have cut the edge, we cut the corner here. So we have 2 points to shorten it. That means we have we have index 2 in any plane. Well, plane means 2 sphere, which is containing this geodesic, gamma tilde. And so how many planes are there? Well, this is the codimension. So the index of gamma tilde of this non-minimal geodesic must be, of this one must be 2 times p minus 1. P minus 1 is the codimension, right? P is the dimension, gamma is dimension 1, so p minus 1. And this goes to infinity if p goes to infinity, of course. And this was only the mildest case. If we have more of these, the index is even bigger, so we have a lower bound. That means if you have a large sphere and large dimension, then all the non-minimal geodesics have large index. And the same happens for P equals SOP and P equals PI SOP, the iterated centrioles. The reason is that also in these spaces, we have a lot of spheres, and we use these spheres. Okay, and now we are in the state to classify all maps from the K-sphere to, say, SOP. make a star here, map star of SKP is the set of all maps phi from SK to P, such that phi composed to mu0 to this first meridian is gamma 0. So one meridian is already mapped to one meridian. This is homotopic, no problem. And similar, we will have map star SK minus I PI. Of course, we need meridians also in S1, S2, and so on, and meridians also in the PI. We call them mu I and gamma. Now, if we iterate what we have learned in section 2, you get a map, theta, which goes all the way from the maps of S1 to Pk minus 1 into the maps of Sk into P0, just by this inclusion, by suspension, by geodesic suspension. And all these inclusions are deconnected, are in homotopy are isomorphisms until the dimension d. And the map maps any element here, call it phi k minus 1, into the k minus 1 fold geodesic suspension of phi k minus 1, which then is homotopic to the original phi which we started with. Right, so we start with a S1 anechoic curve is the image, and we make the geodesic suspension over this curve. Closed curve, geodesic suspension, until we have a map of SK. Now, there are two possibilities for this map phi k minus 1. It could be homotopically trivial, that means contractible, or not. Phi 1 of Pk minus 1 is the first homotopy of this map. So in the first case, we just contract it. We can contract phi k minus 1, and this geodesic suspension then is also contractible. So everything is contractible. Nothing interesting happens. Second case, phi k minus 1 is non-zero. Then it's homotopic to a minimal geodesic. We just can, phi k minus 1 is just a curve, a closed curve. And we can shorten this closed curve. It's just one curve, no problem. We shorten it, make it shorter and shorter until it is a geodesic loop, starting and ending at jk minus 1. But a geodesic loop in a symmetric space is a closed geodesic, because those geodesics in symmetric spaces are orbits of one parameter subgroup. They have no intersection, self-intersection, right? So they can only have a circle. So the phi then, the original phi, is homotopic to a k minus 1 fold geodesic suspension of a closed, minimal closed geodesic. So minimal, of course, means minimal in its homotopy class. And this turns out to be a Hopf map, which we call Hopf map phi tilde. What is a Hopf map? It is a restriction to Sk of the linear map from Rk plus 1 to the set of matrices, P cross P matrices, sending Ei to Ji and Ek plus 1 to the identity. Remember, we have this family of centrioles, which corresponds to a family of to the Clifford family. So we have these Ji. Right, so this is a linear map. We have given a basis, the image of the basis, and if you restrict this to Sk sitting in Rk prime plus 1, so we will also call this a linear map on the Sk by abuse of language. we get what we call a Kopf map. Very special map. It's a round sphere inside the matrix space. Round, totally geodesic and even more. Round sphere, very nice sphere. Now the theorem is, which we have already proved, so to speak, if P is big, the dimension, and phi is not non-trivial, then phi in map SK SOP, then it is homotopic to some phi tilde, which is a Hopf. This is in the paper of Theobald Shapiro, in a different formulation. But there's some problem with this theorem, namely parameters are not allowed. So we are not allowed to replace phi by a family, phi x, because we can do this for any single one, but we have no process to do it for all together. And in fact, not only that we have no process, it is wrong. Look at the space of all closed curves starting and ending at jk minus 1 in pk minus 1. It is a disjoint union of omega s of connected components where s runs through the fundamental group of pk minus 1. Space of curves is of course parameterized by the fundamental group, the connected components definition. Now, for low s, for instance, if this is finite, then all s are low, so to speak, we can find gamma tilde, which is not minimal, non-minimal geodesic, and omega s, but with low index. And we cannot apply our theorem. The index condition may fail on omega s when dimension of x is bigger than 0. It's positive. I mean, if it's 0, if we have just 1 point, it's no problem because we always have, for non-minimal geodesics, the index is always at least 1. But we cannot do better in general. Now we can do better in a special case. Namely, in this case, where the fundamental group is Z. So we have seen this table. This happens precisely when k minus 1 is 2 modulo 4, or if when k is 2m minus 1. It's precisely this one. And then, of course, we need that S, this parameter, which counts the connected components, is if this is large. We will see how large. Here is a theorem, which is not in but here, but in Shapiro in this form, but a consequence, only a topological consequence of this. So let K be 4m minus 1. We are looking for K spheres for 4m minus 1 spheres. And there is a certain number pk connected to this, which is the dimension of the spinners. That means Sk is a irreducible CLK module. There's just one. It has a certain fixed dimension, called it pk. Corresponding to k. And now fix some d, some number d, with a property that pk times d is smaller or equal to s, is smaller or equal to p4, p over 4. So in particular, p over 4 must be large, right? Because it must be larger than this. And there's some space in between. So the s must be rather big, but not too big. On the other hand, this is not very great because p goes to infinity anyway, but this is great. So for low s, we cannot do it. Then the inclusion of the Hopf maps, which I explained here, these linear maps, as component inside all maps as component is deconnected with an isomorphism in homotopy up to dimension d. And here's the idea. And maybe it's astonishing, we had some problems to find this. We do not use the loop space, but the path space again. So in some sense, you just can continue with the old methods. And we extend this map theta, this long map, which we had upstairs here, right, going from S1, S2, and so on, up all the way to Sk. We want to extend this by another member, another map, namely going from S0 to S1, call it theta 0. Well, you can do this. S0 is, of course, 2 points only. And right, and we have in S1, we have just 2 meridians. mu0 is one of them, and mu is the other. So here in this space of map star, the image of the meridian mu0 is already fixed. It's gamma 0, which goes through jk inside, which then determines pk. So this is fixed. But the other mu tilde, mu, can be mapped to whatever curve from jk minus 1 to minus jk minus 1. And then it's straightened, this is this homotopy here, to a geodesic, the shortest geodesic from jk minus 1 to minus jk minus 1. So the picture looks like this. It's not round, there is an angle. The question is, could be an angle. What is this angle? And this, we need quite a lot of time to understand this. We had to understand this structure, in this case, k equals 4m minus 1, very precisely. The first is there is a complex structure around, namely J1 up to the product of J1 up to Jk minus 2. Call it I. It's a complex structure on Rp. And the Jk is just I times Jk minus 1. Could be plus minus, we choose plus. And then our gamma 0 is just e to the I pt jk minus 1. This goes then to through jk. T runs from 0 to 1 always. Now, gamma is also a minimal geodesic from jk minus 1 to minus jk minus 1. What is a minimal geodesic? Well, using this complex structure, we really have an embedding, a nice embedding of our space pk minus 1 into the unitary group. And so, in fact, minimal means then minimal also in the unitary group. So what are minimal geodesics in the unitary group? Between from identity to minus identity, we multiply by jk minus 1 again. And this is very easy. It is of this sort. Diagonal matrix e to the ipt e to the minus ipt with some dimensions, identity in the CR, identity in the CS, for some invariant splitting CP half, which is RP, into a CR plus CS. And then the full loop, because gamma 0, then gamma reversed, looks like this. On the space CR, it is just we run gamma 0, and then we run gamma back, but here on this space, it is again the same trace back. So it looks like this. While on CS, it gives a round sphere, a round circle. It really continues the same way by e to the I pi t. Now, the last step is this part just can be contracted. And so we end up, because we have found the last step, we end up with a Hopf map, and we have proved our theorem that the Hopf maps are deconnectedly included into all maps when S is large enough. Now let me just finish to give the application to vector bundles. Now here's a picture. If you have a vector bundle over a sphere, the sphere has two parts, northern and southern half sphere, E plus and E minus, and the vector bundle, of course, is trivial over the half spheres, over these disks. And so it can be viewed as follows. We have vector space E plus for D plus, fiber, say, at the North Pole, E minus, fiber at the South Pole, which can be identified with all the fibers in the northern half or in the southern half. But then we have to patch these together, and this is done by map phi from the n-1 sphere of the equator here into the SO of E plus E minus. It's an oriented vector bundle, so therefore SO. And this is called the Clatchy map. Now this can be done, of course, for any dimension n, but now we assume again that n, which is k plus 1, is 4m. It's divisible by 4. And let me give an example. If we have a Clifford family on our P, which we now call L, then we look at the product of all J1 up to Jn. Before we had only up to 2 now we take all of them. This is an involution again, and it anti-commutes with all Ji. And therefore, L decomposes into two parts, L plus and L minus, the eigenspaces of W, called the volume also. And the Ji interchange the two because they anti-commute with W. So they interchange the eigenspaces. And these J1 up to Jn in S or L plus L minus define a linear map from the equator Sn-1 to SO L plus L minus in the way I've done it. So EI goes to Ji. And this is called the Hopf bundle. Well, I have not said this notation. E upstairs is E plus phi E minus, right? Phi is a Clatchy map, E plus E minus are the fibers over the North and South Pole. And here we have L plus, mu, L minus. Mu is this linear map, the Clifford multiplication of the line. And by theorem 1, if P is big, then we have seen that all bundles over Sn are in fact Hopf bundles. Now we replace the sphere by a sphere bundle. By a sphere bundle, a special case of the sphere bundle, we start with an oriented n-dimensional sphere vector bundle V. We take its disk bundle dV, take two copies of it, V plus V minus of V, and we put them together at the equator SV, the sphere bundle, which is the same as the sphere bundle of V plus trivial one-dimensional bundle. This is the bundle over X, over our parameter space, which is a finite CW complex. for instance, a compact manifold. And then we can do the same, more or less, but instead so we have again the same thing. We need a map phi now from SV to SO E plus E minus, which is called a clutching map. Now everything depends additionally to a parameter in X. And the same example or similar example as before. Now we need, instead of a Clifford representation, we need a Clifford module. We need a Clifford module bundle. CLV is just the set of Clifford algebras over the space Vx. Vx is a fiber of V, right? So we have a vector space, we have the Clifford algebra over it, and for any x, so this gives a bundle, CLVx or CLV, and we have a Clifford multiplication, CLV tensor lambda to lambda, in any fiber defined. And we put then Ji mu of EI for any oriented orthonormal basis of phi, which is of course dependent on this choice of the orthonormal basis. But if you take the product, it's independent. And the eigenspace decomposition with respect to this W again gives lambda plus lambda minus, and the Ji interchange. And this is called the Hopf bundle corresponding to the given CLV module lambda. CLV module bundle. And now my last theorem is as follows. Any vector bundle over such space.
Just basically,
Yeah, sorry, I'm
you're running out of time here. Could you...
right. May I just say this theorem and then I stop? Any vector bundle over this sphere bundle V hat, it was called upstairs here V hat, is stably of the form E plus L, where L is a Hopf bundle, E is just a bundle over X, and L is a Hopf bundle. And in the case, and there's a uniqueness. In the case when V is spin and M is even, then the L can be written as E1 tensor S, where S is a very special bundle, the spinor bundle. And this will play the role of the Thom class in the theory formulation. I just should say, well, we need the stability. Stability means we can add trivial bundles to E, and we can add CLV examples of CLV, the Clifford bundle, but it can also considered as a module bundle any times in order to get to the stable range for this other S which I mentioned before. So I guess I cannot give anything anymore, but here are the literature, and it only remains to me to say thank you, and I'm sorry for running over time. Thank you very much.
Oh, thank you. Thank you very much. There is, well, are there any quick questions from Zoom, from the room? I have a stupid question. In your theorem 1, when you say, and probably elsewhere too, when you say that P is large enough, is K fixed or P is kind of absolutely has a number?
No, K is fixed.
Okay,
but of course, only we need a bound for K, right? Then,
okay.
Yeah, only this.
Thank you. Other questions or comments? If there are none, let's thank the speaker again. And now we are going to have a coffee break for 15 minutes. And as usual, we have breakout rooms where everyone can gather in smaller groups and discuss something. We're inviting last two online speakers to breakout rooms 1 and 2, but we're not so crude to ask Professor Berestovsky fight this interface. But Valery Nikolaevich, are we with us? No.
It's not with us.
Oh yeah, he's not with us. So, can you, could you please first stop your demonstration so we can start the next one? I mean,
Yeah, that's difficult for me, sorry. Yeah, okay.
yeah. And second, could you spend some time in breakout room 2 so that if someone wants to
I will try this.
discuss something with you privately or have some questions. Nope. We are displaying the schedule for now. Ну что там с брейкаутами все произошло?
В смысле, что инвестиционные залы, у них кто-то вот. Да.
Пошел на что-то желающих обсуждать домотопические
Do you hear me?
Yes,
Good morning.
only it's 2 minutes more.
Yeah. But I just wanted to try. So it seems sharing screen is working nicely. So I can move the pages. So okay. Thanks. Yeah, it's too bad that this is online now. Most events are made online. That's really bad.
Yeah. We hope for more offline participants, but not so easy these days.
Yeah.
Ring the bell one more time. So, we continue our morning session, and the next speaker today is Philip Leplock from Sorbonne, and his title is here, Recent Advances on Einstein Equations, asymptotic localization and gravitational singularities. Please.
Thank you very much. It's a pleasure to be talking in this conference. As you will see, the main result I want to talk about is about geometric analysis, prescribed curvature problem, and constructing the global geometry of certain solutions to the Einstein equations. So this is my main goal, and it will be part of Riemannian geometry. But to present it, I need first to talk about Lorentzian geometry a little bit. So the goal behind it is to understand solutions to the Einstein equations, so space-time satisfying certain curvature conditions. But inside this big problem, I'm interested in the constraint equations of Gauss-Codazzi Z type and analyzing the global geometry of solutions. In recent years, I've been going into two directions to reduce the decay of solutions at infinity. So this is a very important issue in general relativity. And another issue, which is maybe less standard, but I think extremely interesting, is to have low regularity on the metric. And sometimes some of the results will be even with weak regularity, allowing for gravitational waves, certain singularities or localized singularities in the spacetime. For today, the main result I'm going to talk about is joint with Nguyen in Paris and concerns the geometry with low decay and the construction of solutions to the Einstein equations with certain prescribed asymptotics at infinity. So what we want to do here is to revisit the notion of asymptotic flatness in Riemannian geometry and especially in general relativity. There is a second topic, probably I will only browse through it at the end, which has to do with construction of singular geometries. And what I've done with Bruno Le Floch in Paris and Gabriele Veneziano in Geneva is to revisit certain notions of junction across hypersurfaces in spacetimes. And the motivation, the physical motivation behind this question is to define cosmological spacetimes beyond singularities. So this is a bit, an unusual problem, but it's also quite interesting to understand what rules should be imposed on the junctions when you have a singularity of a Big Bang, Big Crunch type, and yet you want to cross this singularity in a way that is geometrically satisfactory and physically satisfactory, and even also you can do some analysis on it. So this is a goal, and as I said, the main topic will be the first topic. So I want to show you a result of existence of Einstein solutions, where we prescribe the decay at infinity, and almost arbitrarily, in a way that is very unsymmetric. So it goes very much beyond what I'm going to show you first, which are standard results in mathematical general relativity. So the topic has to do with Lorentzian form manifolds, solving the Einstein equations. So you have on one side a Ricci or the scalar curvature, and on the other side of the equation, you have the contribution from the matter. And you are, in this setup, you are interested in solving the initial value problem. If you know the geometry on a space-like hypersurface, can you predict the future geometry based on the data that you put on this initial geometry? And what you need to prescribe for this initial value problem is a Riemannian 3 manifold with certain asymptotic properties like I'm going to discuss. A metric comes with that. And there is also the extrinsic curvature of this hypersurface inside the 4 manifold. And as we know it, there are certain Gauss-Kodadzi equations that must be satisfied. And the main goal of my talk today is to analyze the so-called Hamiltonian and momentum Einstein constraints equations, which you see below. And they have to do with the scalar curvature of the manifold, the Riemannian manifold, and some condition about the divergence of the extrinsic curvature, which are prescribed. And if you prefer, you can think of rho zero, which describes the mass content of the space-time. You can just take it to be zero. Well, everything I will say is as almost as interesting. And you can also take G0 to be zero, which describes the momentum, the speed of the particles in the space-time, if you wish. So for this initial value problem, there are a lot of results, some recent for Schwarzschild or Kerr, which consist of taking a more or less trivial solution of the Einstein equations. So by that, I mean Minkowski, Schwarzschild, Kerr, some maybe other solution like De Sitter, and adding some small perturbations on an initial hypersurface. And can you prove a global existence result for the Einstein equations and therefore construct a small perturbation of the given spacetime? So somehow this is not my interest, my main interest, because I'm interested in looking at solutions that contain some effect of the matter, or you could say non-Ricci flat solutions. I'm also interested in allowing asymptotic symmetry, which is not spherical symmetry as it is used in all previous works, and finally allow for singularities in the geometry. So all of that are questions that have to do with the global geometry of spacetimes, and that goes very much beyond what is currently done in the field. And of course, to make some progress, you have to look at specific questions, specific problems. So this is what I have done. Sometimes for some of the easier problem, I started imposing some T2 symmetry, for instance, with two space-like Killing fields. But the results I have in mind here, the first one with UMA is the stability of Klein-Gordon fields. So you have a space-time. The space-time is not Ricci flat, and still you want to prove some stability property. That's what I can show you first. The second result is to study the Einstein constraint beyond spherical symmetry. This is the main result I want to discuss today. And there are also questions I've been looking at where you allow hypersurfaces in your space-time the hypersurfaces themselves may be irregular, but the geometry as you approach these hypersurfaces, this geometry is singular. So again, as I said, I'm not going to enter in this last topic very much. So what I do is that I show you one slide about the evolution, this nonlinear stability of non-Ricci flat solutions. Just one slice about that, because this has to do with hyperbolic techniques, and that's not what I want to show today. And then I move the rest of my lecture to the Einstein constraints. So for this evolution problem, what you have to keep in mind is that there is very rich and complex dynamics. So if you perturb a solution, a trivial solution, say, to the Einstein equations, it's quite hard to decide whether the solution will decay if you maybe linearize the partial differential equations that you deduce from the Einstein equations. It's quite technical, hard to figure out if you would have some decay in time or in null directions, in time-like or null directions. And in addition, there is also this issue of what is the behavior of your manifold, of your initial slice, as you go to space-like infinity. So the way the geometry will decay or not is essential in order to describe, to determine the global evolution of this. So on this problem, there are two independent proofs in the last 3 years, one by Ionescu and Posoder, and one by myself and Yuma, which is what I just sketched on this slides, but it really takes 150 pages to prove the theorem that I'm showing you now. So the theorem says that. The theorem says basically that you have stability of a Ricci flat solution beyond the Ricci flat regime somehow. Of course, the perturbation has to be close to some reference solution, which I'm taking here to be the Minkowski space. So I'm taking the Minkowski space, I do a small initial perturbation beyond the Ricci flat regime, and I'm asking what is a global evolution of that. And so our result says that modulo certain decay conditions at space-like infinity, which I'm going precisely to discuss in a few seconds, and going beyond spherical symmetry, provided this initial data satisfies for the Einstein constraints, I can prove that the initial value problem for the evolution Einstein equations admits a globally hyperbolic Cauchy development, which is foliated by asymptotically flat hypersurfaces. It is future causally geodesically complete, which means that an observer in this spacetime going to infinity in his foliation will live forever in some sense. The asymptotics in time is also very well understood, and basically the small perturbations that you have put initially disperse and goes away, and asymptotically you reconverge to Minkowski spacetime. So it may seem like a small result, but in fact, first of all, it builds upon earlier result by Christodoulou, Kleinerman, that I quickly mentioned on the previous slide. And it adds, in addition to all their techniques, we add for this result the challenge that the equations are no longer invariant by scaling. So this is the main challenge for this proof, is to work out a proof of stability for a huge system of nonlinear wave equations, where you want to rely on the symmetries of Minkowski space because they represent certain asymptotic symmetries for your actual spacetime, but you're not allowed to use a scaling field that all previous works were using. So this is the new part of this work, and the way that technically we do that is by introducing a foliation of the spacetime, which is asymptotically Euclidean outside a certain cone, where you could think that the initial perturbation within which the initial perturbation is propagating in a certain sense. And inside this cone, we need to use a completely different foliation, which is a foliation that we can define in Minkowski space by hyperboloid, which are space-like hyperboloid defined within a cone. And we do that by defining the similar object, which are asymptotic hyperboloid or asymptotically Euclidean. And the proof has to do with deriving certain estimates for the decay of solutions. So there are Sobolev inequalities, RD Poincaré inequalities, but all these inequalities must be revisited because they must be stated on the foliation, on the slices of the foliations that I just sketched by the picture. And another ingredient in the proof is to handle the coupling between the nonlinear geometry, which people were somehow doing before by analyzing Ricci flat solutions. But now we have, in addition to that, we have to understand how this geometry couples with the matter. So there are certain interaction terms that may make the solution to blow up, and you have to control them in a uniform way, to have decay in time. And I think the message I want to bring here is that the decay in time that you can prove very much depends on the decay in space that you have assumed on the initial data. So now comes the main problem, which is to construct Riemannian manifold, which are asymptotically flat and contains a rich structure at infinity. So this is a goal of this work with Tikan Nguyen, where we have a problem where the scalar curvature will be prescribed in a certain way. I mean, the Einstein constraints are a little bit more complicated than prescribing the scalar curvature, but they are in the same spirit. We have a manifold. This manifold may have possibly several asymptotic ends, but if you think of one asymptotic end, and this is what I will state, this is good enough to understand the result. We will be looking for a Riemannian metric on a Riemannian manifold. We also look for a symmetric two-tensor field K representing the extrinsic curvature. And in addition, since we are not only looking at Ricci flat solution to the evolution Einstein equations, we also prescribe certain matter fields. I call them H star and M star. And so now you see the equation that we want to solve. Scalar curvature plus a trace of K square plus a norm of K square is prescribed, possibly zero if you prefer. And then you have the divergence of K minus trace of K times the metric, which I'm going to call, I give a notation to this quantity, I call it H. So H is roughly like the extrinsic curvature, but shifted a little bit. Now you have two differential operators that are behind this problem, which I call H curve H and curve M. And these are the operators I need to analyze. And I need to analyze these operators and actually their linearization and their dual. So this is what we will see in the various statements or sketch of the proof that will come now. So sometimes I use this notation G curve for H curve and M curved. So the earlier works on Einstein manifolds, Riemannian manifolds, are mostly in a vacuum case, compact manifolds with fast decay to Schwarzschild. So Schwarzschild means that your manifold is spherically symmetric at infinity, asymptotically. So it depends only on one parameter. There's a mass parameter that comes in the definition of the Schwarzschild metric. There are two techniques, a conformal method, which consists of making some ansatz on your metric, on your second fundamental form, and looking for solution with a certain ansatz. The story starts with Lichnerovich. And here, I'm really sorry that I do not know the Russian literature I would be very happy if one of you could send me, some references that would be relevant and which I'm just unable to cite today. And so there are two techniques. The second technique is a technique I want to develop, the variational method. And it's much more recent, but maybe more interesting for the Einstein equations. And it has been introduced by Rick Schoen and developed by Corvino and more recently by Alessandro Carlotto and Rick Schoen. And I'm going to rely on their recent works that goes back maybe 5 or 6 years. And what I present today is a generalization or some improvement of what they have done for a slightly, a different problem, but really I'm following the same line of ideas. So the method I propose, I call it the seed to solution method, and you will understand in a second why I call it in this way. So we are interested in the global geometry of solutions to the Einstein equations in the Riemannian setup. In general relativity, when interested in certain conditions at infinity, typically you want to say that nothing will influence your solution inside. So asymptotically flat is really a typical assumption that you want to take if you are in a non-compact case. But what the physics doesn't really tell you, or the geometry does not impose you, is the actual asymptotics at infinity. So this is what I want to do here. I would like to basically prescribe the asymptotics arbitrarily and then construct the solutions to the Einstein equations, which is consistent with these asymptotics. And more or less, I cannot say that it is unique, and I guess it's probably not unique, but more or less, I would like to have a map. I construct a map, a seed-to solution map that takes the data at infinity, prescribed data. It's really like like you would do for an elliptic problem on a bounded domain, right? You put data on the boundary and construct a solution inside. So this is what I do, but of course the equations are much more involved, and we do it with data at infinity. So the way we proceed is to pick up a seed data, meaning a good ansatz for the solution at infinity, which you could think of constructing by by formal expansions. Also, this is easy to produce. So you have certain ansatz at infinity that give you first approximation of the actual solution of the constraints that you want to define. And this seed data will be classified in tame or strongly tame seed data in a way I will discuss. And basically, this has to do with the nature of the decay or the ways that the ansatz is satisfying the Einstein equations or not. Based on that, we built by a suitable fixed point argument a solution to the Einstein equations. But somehow we go beyond that. We analyze these solutions at the harmonic level of decay. So this is the main technical issue here is not so much to construct the solution, but is to have a very good understanding of the geometry at infinity. So this goes through what we call quantitative estimates. And it's also very much connected to the problems that was actually solved. One problem that was solved in the paper by Carlotto and Schoen, which they call the localization problem. So I have a picture to allow you to understand. And the picture does not actually, I realize it now, it doesn't actually describe what they have done, it describes what I have done. And I have two pictures that are slightly different. So you have to somehow modify the picture to understand what Carlotto Schoen have done. And maybe I tell you that in a couple of minutes. So basically, I want to construct something that is asymptotic, maybe Schwarzschild, asymptotic Euclidean. There may be a narrow angular region concerning the ways that you connect them. So I will be more precise in a minute. But anyway, all of that has to do with the asymptotic geometry and proving critical elliptic regularity estimates at the harmonic level. And there is a notion of mass correctors that will come also. Oh, okay. So this is just an overview and what I actually want to show you. And so comes now a couple of theorems. So the first theorem says that if you give me a seed data that is somehow good seed data, in a sense that I can measure how close it is to the Euclidean metric, or how close the extrinsic curvature is close to be zero, to go to zero asymptotically. So these are given by the first two conditions, G1, H1. But in addition, I also want to test how good these data are satisfying or not the Einstein equations at infinity. So I look at the Hamiltonian operator and the momentum operator, and I look at their decay at infinity. And I introduce certain power, which I call PM. M stands for matter, if you like, and PG stands for the geometry decay. And so based on that, I'm able to construct an actual solution, GH, to the vacuum Einstein equations. And then comes the interesting part, which is depending on the prescribed data, what can you actually prove on your solution? And it's interesting to see that if you have a seed data that satisfies the constraints at the order, which is not harmonic. So harmonic would be PM equals 1. But you assume that you have done a good job somehow of getting your ansatz, but not at the level of the harmonic level PM equals 1. Then the theorem tells you that you can actually construct a true solution which has exactly the ansatz that you prescribe, G1, H1, but you don't include 1 over R in this statement. You cannot. Now you have the situation where you have done your ansatz with such quality somehow that PM can be taken to be 1. So if I compute the Hamiltonian, the momentum, somehow I will find terms that reflect contribution 1 over R of the metric. And that actually means, because you have two derivatives, it means that the error will be of the order of the exponent minus PM minus 2, PM equals 1 that I wrote. So if you are in this setup, if you have certain integrability of the momentum and Hamiltonian at infinity, L1, then you can prove that your actual solution is asymptotic to G1, H1 that you have chosen. But there is one extra contribution, which I denote by M tilde R square Hn of 1 over R, which is some kind of contribution of a mass at infinity. And this is how I call it. I call it a mass corrector at infinity. And I can actually tell you the value of this mass corrector. Or more precisely, I cannot tell you exactly what it is, but I can tell you that it is roughly the integral of the Hamiltonian plus a higher order correction in terms of the size of these quantities. And then there is a third regime where PM is greater than 1, where you get a similar statement, but you use the error contribution, instead of being a small O of 1 over R, it becomes a big O of 1 over R with a bigger power. So this statement is really the spirit of all I've done in this direction, with now a lot of additional work we can do, which is now to discuss this mass corrector at infinity. So I want to emphasize that this mass corrector only depends on one single parameter, which is a global parameter. So this should, if you know anything about general relativity, and even for Riemannian manifold, this is relevant, it's a notion of ADM mass. That's the notion of mass. So of course, this M tilde has to do with the ADM mass of the manifold, and in a way, this is a correction, and we have actual formula to show that it's a correction to the ADM mass. That it's a mass that you had on your seed data that somehow was a spurious mass inside your metric that by our process was propagated to infinity, and it was a contribution that should come into the DM mass. Okay, I'm not sure I state it in a very clear way, but this is roughly the idea. I will skip this slide, and you can look at it later if you wish. But this is basically what I was telling you by reading the theorem, except for the fact that I did not insist on the fact that the exponent for the geometry, how the metric decay, we allow decay, which can be 1 over r, which is somehow the fastest decay representing the Schwarzschild decay. But we can also allow a decay that is only 1 over square root of r. And if you know about the mass of manifolds, the ADM mass will be finite if the decay is slightly faster than 1 over square root of r. And in the theorem I stated, I did not include this case, but in fact, we can include this very limiting case. So our theorem can also produce solutions that have infinite ADM mass, which may be interesting geometrically. Physically, it's not so interesting. So now I show you, I guess I have to go a little bit faster, but I show you some ideas about the technique of proof. So what you have to do here, you have a problem with prescribed curvature, and this problem with prescribed curvature has to be linearized around our seed data, which is called G1, H1. So here I show you the linearized Hamiltonian. Then I show you the linearized momentum. So these are the basic Einstein equations in linearized form. The first one is a scalar equation for where the unknown is a tensor. It is second order. It's basically the Laplace operator of the twice of the metric, and then you have divergence of your metric perturbation. The linearized momentum is vector valued. The unknown is this H2, and then you go to the adjoint, and the structure somehow is somehow inversed. And these are the equations that you have to solve. And so what we do is here in this work, we do nonlinear elliptic regularity estimates based on, there is a work that maybe you may know by Douglas and Nierenberg in the 50s, interior Hölder regularity estimates for elliptic operators. But, so this paper is useful for us because they analyze systems of different orders. And that's really what we have here. It's a systems, and the coupling is somewhat subtle, how the equations are coupled together, and looking at the dual also produce a system with somehow a quite involved structure. I told you that there was a variational framework. This framework is expressed in weighted space. You look at the Euler-Lagrange equation for this functional. You have a kind of energy functional that you have to minimize. And the fixed point formulation is based on these linearized and dual linearized operators in certain weighted spaces of Sobolev types. And eventually you have to prove Poincaré Korn inequalities in this situation and take care of harmonic terms. So all the challenge is like in the last line of this talk, to understand the slide, the mass corrections, and they come from properties of the kernel of the image of these Einstein operators. Okay, so I realize that the time is going fast, but I guess it's good if I don't go too fast. Now I'm in the remaining time. Now I want to make the connection with the work of Carlotto and Schoen and tell you in what sense I have solved a problem that was raised by Carlotto and Schoen. So what they define is a so-called optimal localization problem. So I must have a picture. This is a picture below. And you see what they do. They take asymptotic infinity and they decompose in 3 angular regions denoted by CA. So there is a cone of a certain angle. So think of A to be, I guess, maybe very large in the picture I made here. So you have a very large cone, a very large angle, where I insist on having my solution to the Einstein equations to be exactly Euclidean at a certain distance. So if you think of being an observer and you think of that in terms of relativity, and if you are in this region, everything will be flat. There will be no interesting geometry. Everything will be flat. And now there is another angular region, which I call this A plus epsilon complement. So it's a complement of the same cone, but a slightly, you have to allow a small transition region. And in this region, I'm imposing the metric, or Carlotto and Schoen are imposing the metric to be exactly Schwarzschild at a certain distance. And then what they do is they solve the Einstein equations in the transition, which I call with a gray, in the gray color, and they solve in this region, and they construct their solution in this region, and they paste it with a trivial solution outside, Schwarzschild or Euclidean outside. So this is their main work. But the result gives you a decay of 1 over Rp, where P can be less than 1 in their analysis. They cannot prove 1 or beyond 1. And so then they ask the challenge whether they could construct the same solution with 1 over R decay in every direction. So this problem is still open, and there is a possibility that it's just not possible to prove that. So what I have proven is something that I've slightly modified in comparison to their problem, which I call the asymptotic localization problem. So what I'm going to ask is that I have asymptotic localization to be Schwarzschild or Minkowski, or actually anything you like to choose asymptotically. But I'm asking that this asymptotic is satisfied, which you see in red. So G is G Schwarzschild or G is G Euclidean in a certain cone. Right, so yeah, the first 2 cones will be Euclidean or Schwarzschild. And you see that the exponent Q is greater than 1. Okay, so it means that asymptotically you are really very close to Schwarzschild or very close to Euclidean. And from a physical perspective, it's really the same problem as saying that my space-time is exactly Euclidean, since you can approach that with any rate of decay you wish, because we could go beyond this analysis and go even beyond, but we cannot make it to be exactly Schwarzschild or exactly Kerr. And I believe there is a good reason for that, but we cannot really prove it. And so what we do here is that we refine. Do I have 1 more minute?
One is okay, even more than 1. Well, I think you have 4 minutes without any issues.
Oh, okay. So you say 4 minutes, so definitely I can finish this discussion. So how do we prove this result, right? So we basically reuse the techniques that I described first, but now what we do is that we design seed data with certain parameters. So you realize that there is a mass corrector at infinity that cannot be avoided. I think it's really part of the problem, and it corresponds, as I try to explain, to a kind of mass that was everywhere in your seed data and that you propagated, but at infinity it only produces a scalar quantity. So it's not, it's not such a big deal, but it is there. So the only thing you can do is to move this quantity away somehow. I mean, to move it. So this is what we do here. We want to move this mass corrector in a narrow region, in this narrow transition region. And how we do that? We do that by picking up a different seed data. So there is a seed data that you want, that you say Schwarzschild or Kerr. So you know what you would like to reach. But the way to reach your aim is to start slightly off. And so we have a formula here that gives us a modification of the seed data that you would naively introduce. And in particular, you see that we have an effect of a psi that lives on the two sphere at infinity. We have also a phi that lives on the two sphere at infinity. And somehow we will use this phi and psi to move this mass corrector around at infinity. So I guess the formula may be a little bit to grasp, but you know, so conditions that we have is that phi should be one except in the transition, but outside it should be one outside the transition. But in the same time, we need the integral to be zero. So you see with these two conditions that we need some transition to make the integral 0 and 1 outside. And then there is a psi, and this psi is 1 in one of the cone and 0 in the other cone. So there's a certain cutoff function that comes at infinity. And again, we analyze the linearize joint Einstein equations around this new ansatz. We compute the correction at infinity, and we use some kind of implicit function theorem in order to determine the parameters. Okay, so that basically, I think, the end of that, and I just conclude in a few seconds to say that there is a second topic that may be of interest to some of you, analyzing bouncing cosmology and understanding how you cross, because it's really a geometric problem, how you cross a singularity hypersurface, and you again analyze the Einstein constraints. This is really the same kind of question, how the constraint should be analyzed, should be parameterized, and so you have to do that in order to understand how to jump and to make a jump that is consistent geometrically and physically. So I will stop here. Thank you very much. I think the slides will be on the webpage, so if you want to browse through this part, please do, and send me an email if you have any question or any comments, and especially references to the Russian literature. For the second topic, of course, I know about the BKL theory, and I built very much on that, and hopefully at another time I will be able to tell you about BKL expansions and stuff like that. So thank you again very much for the opportunity to talk here.
Thank you very much for your talk. Are there any questions, comments from Zoom?
Yes. Can you tell us about your gluing methods? What are you using there specifically? What analysis?
Gluing, you mean for this section 3?
Yes.
Oh, yeah. Oh, yeah, definitely. If I can tell you, let me say, basically the gluing is done by prescribing a map, which we call singularity scattering map, that takes data before the singularity to data after the singularity. We think of a hypersurface that is space-like, and so we move forward in time. But in fact, the same problem can be addressed for a time-like hypersurface. But let's think of it to be space-like and to jump forward in time. So what we say here is that we need a map to do this junction, and this map must take data before and after the singularity. So there are like two issues. I mean, first issue is what sort of data you need. You approach the singularity, how you describe the geometry as you approach the singularity. And it turns out that there are such objects that comes naturally, which will be, would be a metric, a Riemannian metric on a manifold. It will be something that plays a role of the extrinsic curvature, I mean the K, but it has been rescaled. Everything has been rescaled here. But it's basically similar to the Einstein constraint, a metric G, extrinsic curvature K, but now the constraint takes a different form. trace of K should be one, the norm of K should be related to the matter content of your spacetime, and the divergence of K should be prescribed to the matter content. Maybe the last one is very similar to the one I wrote for the momentum constraint, but the Hamiltonian constraint is a bit simpler. So one task is to analyze these equations. It's not very difficult, but you have to analyze and to have a good understanding of this. And then comes the question of how you do the gluing. So the gluing is through a certain map. So you could say I take any map and I do any gluing, but that's not very interesting. So geometrically and physically, the main question is what kind of gluing you're allowed to do. So you glue constraint, solution of the constraint, to solution of the constraint, what sort of gluing and how you parameterize that. And this is the main result of all our work here, which is to say, we have a classification of all sort of reasonable, geometrically or physically reasonable junctions. So you say, okay, there are all these possibilities of junctions, and then you analyze what is possible. And it's fascinating to see that with little restriction on, so basically this slide is telling you that with a little restriction on what you allow yourself to do for the junction, you have actually very little possibility to do the junction. And so we have junctions that we call isotropic bounds or non-isotropic bounds, and they are described by, I would say, a few parameters. I mean, the parameters could be functions or tensor, but this is completely classified. And if you have that, then you go back to the physics, because this is also something I do, and you ask physicists how they somehow regularize the Einstein equations. And then you try to connect the degrees, the few degrees of freedoms that you have discovered here to information that comes from certain specific models. So please, if you are interested, look at the papers that I quote here and in the end. And, okay, so sorry, I've been maybe a little bit long in answering your question.
Thank you very much. That was very instructive.
Thank you. Other questions?
May I ask, are there similar results for Ricci-Soliton equations? Is it correct?
Yeah, I didn't. Right, I know the Ricci-Soliton will be, similar looking equations, but I've not worked on them. So I've read some papers, when Perelman showed his results, but really I cannot answer that. But this is probably a very good question, and techniques that have been developing here could possibly apply to show the existence of Ricci-Solitons. I won't be surprised of that. I think this is a very good question.
So, other questions or comments? Since there are no, let's start
Thank you again.
So we have a lunch break now until 3 Moscow time, and as usual, we invite last online speakers to breakout rooms. So Philip, if you go to breakout room and in Zoom to breakout room 1 and wait for several minutes, and so in case someone will want to enter and discuss further details, then we'll be fine. Another thing is that we're going to fix some equipment here, but we will try not to lose anyone's connection. But if we do, just reconnect and now I think it'll work. So the chairman problem.
Так. Я ничего не слышу.
Не, ну еще есть 3 минуты там.
Давайте. Раз, два, три. Что происходит?
Так, в зуме кто-нибудь ответит, слышно, не слышно?
А мы услышим, вы подключи, вот звук же выходит из вашего
Нет.
ноутбука. Вячеслав.
Пока нет.
Нет, ну как бы звук выходит. Мы услышим ответ.
Слышно вас.
Ага, хорошо, спасибо. Good day, dear friends, dear colleagues. Let's start our section again. Our next speaker is Daniil Mamayev, St. Petersburg State University. He will talk us about Morse index retrieval. Please, you are welcome.
Thank you. Yeah, first of all, let me thank the organizers for the opportunity to speak at this Chamber yet Reaching Quantum conference. I will talk about Morse index retrieval, and it's a work in progress on the supervision. Okay. Oh. Yeah, and it is a work in progress under supervision of Gaina Irina Panina. The results so far can be found on archive. I have the number written somewhere. And I will start by formulating. Can you see what happens here at this side of the, yeah? Okay, so I will start by formulating the problem. So suppose we have a unit ball and a smaller ball inside it. So we call the smaller ball U, and this area is the unit ball minus a small ball. And we have a function f, a smooth function on this annulus, well, multidimensional annulus to real numbers, smooth function without critical points. Huh? It doesn't really matter. Let's say closed. Yeah, let us consider the space of all extensions of our function small f to the whole unit ball, smooth extensions, such that, well, first they are extensions. Second, they have a unique critical point, which is at the origin. This is the origin. And third, the critical point is not degenerate. So the form of second derivatives at this point is non-degenerate. And to each such function, there correspond a number, lambda f, the Morse index of the origin with respect to function f. So it's a function from the space of all the extensions to numbers from 0 to n, which I will abbreviate like this. So yeah, and let us consider the set of all the possible indices of the extensions of our function small f. And the problem we are interested in is what the set lambda f can be. So like what subsets of the set from 0 to n can be the sets of indices of the extensions of some function defined in this annulus.
What is n?
N is the dimension of the ball.
Can the index be larger than the dimension?
No, it's from 0 to n.
Yes. It's non-degenerate critical point.
Yes, it's a non-degenerate critical point. Okay, so let us make some simple observations. First, let us know that the parity of the indices of extensions of the same function, they must be the same. So either they are all even or they are all odd. Well, it's easy to see, but let me prove it nonetheless. how you do this. Okay, so first let us pick a metric. Is a remaining metric in the unit ball such that, yeah, well, first let's take a function. Then pick a metric such that near the boundary, our metric is standard. So like the standard Riemannian metric in Rn. And near the critical point, near the origin, well, as our function is Morse, there exist coordinates x1 to xn such that f is the following quadratic expression. So first you have lambda negative squares, then you have the rest are the positive squares I from lambda plus 1 to n positive, and you want your metric besides that the gradient with respect to this metric of the function f is what you would expect the gradient to be. So it's minus 2x1 blah blah 2xn. Okay, so you picked a metric. Now, yeah, let us look at our function more closely. So in this coordinate, let us consider a small sphere around the origin. It's something like this. Is the sphere, well, sum of xi square equal to epsilon. And connect the sphere to the exterior sphere by an isotropy. So you connect it, and you get an isotropy from the product of the sphere with the interval to the ball. And let's look at the function v equal to the gradient at point h of xt divided over its modulus. Well, it never vanishes since there are no critical points other than the origin. So you get a function. Oops. So you get a function from the unit sphere. From the product of the unit sphere and the interval to the unit sphere. And so the degree of this function on the outer sphere is equal to the degree of this function on the inner sphere. But as our function f is just a small f near the boundary, this degree on the left depends only on the initial function small f, only on f. And this thing, well, you have your function is a standard in the neighborhood of the origin, and the gradient is standard in the neighborhood of the origin. So you just do the simple computation for this function and this gradient vector field, and you get that this degree is equal to the minus n to the power n plus the index. So you see that, yeah, the parity of the index depends only on the initial function f. Okay. Similarly, you can see that if f can be extended to the unit ball without critical points, then there is no way to extend it with only one critical point. Then lambda f is the empty set. Also, yeah, lambda f can be just a singleton. How to do that? Well, just consider this function. So let f be this function, the standard one.
Sorry, what is f small? What's
Sorry?
f small? What is f small?
What is F small?
F small is a function in the multidimensional annulus. I don't know how to, the spherical shell, which is between the unit sphere and the small sphere around the origin.
What?
Yeah, if your function f is like this, then of course you can just by the same formula. What? Then of course by the same formula you can extend it such that it will have index lambda. So obviously lambda is in lambda f. To prove that no other index can be obtained is, well, it's not very hard, but you need to prove that it's indeed a singleton. You need Morse-Baranikov complex. Morse-Baranikov complexes. So you just look at the canonical form of the corresponding Morse-Baranikov complex, and you see that indeed the function can be extended in any different way other than with index lambda. I will probably speak about Morse-Baranikov complexes in some details later. Okay, now the main result. The main result is that for any dimension, which is at least 2, and for any lambda, the index from 0 to n-2, there exists a function small f such that the set of possible indices of its extensions consists of exactly 2 indices, lambda and lambda plus 2. And yeah, let me give a sketch of the proof. In dimension 2, yeah, so you basically apply some theory to construct such function. So you start.
So then, if n equals 2, then you're going to construct a function with 2 different extensions, one with minimum
Yeah.
at 0 and
Another,
another maximum.
yes.
Without other critical points.
Yes.
Okay.
Okay. Yeah. So yeah, in 2 dimensions. Yeah. The question is basically like, suppose you are wandering in a fog, and the question is whether you can tell a mountain from a crater by wandering around. And the theorem says you that, well, not necessarily. In some cases, for some types of landscape, you cannot tell crater from a mountain. Okay, so let us start with a function of 2 variables, which is simply the height function, the second coordinate. So there are 2 critical points. Yeah, and let's look at its restriction to the unit sphere. There are only 2 critical points, the North Pole and the South Pole, and the gradient points up at both of these points. Okay, now let us transform the circle into the following figure. Not changing the function. The function is still the second coordinate. So you look at this figure and you see that there are 4 critical points now. the gradient still points up at each of them. Okay, it was one way to transform our circle, and the other way is to do it like this. So yeah, still 4 critical points, but now, well, here the gradient it points out at the newly created critical points, and here it points in. Okay, now let me take some colored chalk. Yeah, and let us put a point of maximum here. So you and change the curve. So what you do is you take a point of maximum. So everything points to this point, at least in some neighborhood. And in this fashion, we exchange this critical point for this critical point. And what's the difference between this one and that one is that at this critical point, the gradient points out, and at this critical point, it points in. And similarly, so, and here, let me also write what is minimum with maximum. So here is local minimum, local maximum, local minimum, local maximum, local minimum, local maximum, local minimum, local maximum, local minimum. And we inserted a point of index 2, right? And at the lower picture, let's insert a local minimum. So a point of index 0. And you replace a critical point with the gradient pointing in, the critical point with the gradient pointing out. Still a local minimum. There's still a local maximum. Okay, let us now do a diffeomorphism of the picture so that the inserted critical points go to the origin and the curve is just the circle.
I don't get it. If the gradient goes down, then would local minimum change?
No. Why would it? I mean, like here it goes in this way.
You originally the gradient go out, but then you add this red piece, and on the top of the red piece, the gradient is pointing down.
Mm-hmm. Yeah. Okay. So, well, in fact,
it looks like on the top picture, the top red point is the local minimum, because the direction where it grows, it's kind of.
Well, it's not.
Oh, okay.
I mean.
Okay.
Well, in fact, like you can do this in such a way that your function, like your function at this piece and at this piece is the same. So yeah, well.
Please mention that this is Baranikov trick. Just you should refer. It is Baranikov trick, isn't it?
Yeah, it's a lemma by Baranikov, I guess. Yeah.
Okay.
Baranikov 94. Yeah, sorry for not mentioning him yet. I will do this lots of times later.
And actually,
yeah, so
the function does not change. The function on the circle does not change.
But the extension to the neighborhood changes, right?
Yeah.
Yes, the extension in the neighborhood it differs. Yes.
Like yeah. Okay, so now you do a diffeomorphism and you place the critical points into the origin, and well, let's say you put your critical points of the restriction like this. So it's 1, 0, 1, 0, 0, 1, 0, and the gradient points first 2 times out, then 2 times in. So these 2 functions, they look quite similar near the boundary, but well, they are not the same. There is no reason for them to be the same. So to actually construct a function that can be extended in 2 different ways, with index 0 and index 2, you need a further step, and this is the following. Let us put these circles concentrically like this. So yeah, let it be, well, this is the unit sphere, this is half of the unit sphere. And inside the smaller ball, yeah, let us denote this function by f2 and this function by f0. So inside the smaller ball, we have the function f2. And near the boundary of the larger ball, we have the function f0. Well, not quite. First, it's not f2, but f2 composed with something like 2 multiplied by something. And second of all, f0, we replace it with a composition of some diffeomorphism such that the values at the corresponding critical points are coherent with the gradients. So here we want the value to be smaller than here. Here the value should be larger. Here the value should be larger again, and here it should be larger is this way, and this way, yeah. And here it should be smaller. Okay, so L is a diffeomorphism of the real line, making this function f0, well, just shrinking it this and that way. And yeah, so, and it turns out that if we have such a picture, then we can actually find a function g, such that a function g from the unit ball to R, such that near the boundary it agrees with function f with our modified function that can be extended with index 0, and near, well, not near, but in the smaller ball, it agrees with, well, the function f2, well, modified slightly. And, well, we are done. Then, well, it's a smooth function. So, yeah, let's take small f to be g restricted to some thin layer near the unit sphere. So something like, well, I don't know. And then if you take the extension of f small to be g, then it has index 2 at the origin, and as g agrees with, so it's the same thing as L composed with f0 near the boundary, and this function can be well, it has the critical point of index 0 at the origin. So we are done. That was the sketch in the 2-dimensional case, and let me comment a little bit about what we should do in high dimensions. So, yeah, first step. Yeah, first of all, well, you can't really draw these pictures in high dimensions, so you should insert your points like by simply writing formulas. And for this all to work, you need to insert this pair of points and this pair of points on the same gradient line. So, well, here in two-dimensional case, there is only one gradient, well, two of them, but yeah, well, they are on the same gradient line going from this global minimum to this global maximum. And in the multi-dimensional case, you should keep it this way. Then, well, inserting of critical points, yeah, you can also do that. Yeah, and you want your function, the restriction of your function to the boundary to remain the same. You can do that. Then you don't need this step because you never changed your boundary. You were changing the curve. And yeah, also when inserting this pair and this pair, you should make sure that the gradient lines they remain like similar. That the picture of inserting, like you inserted somewhere here two critical points and somewhere here two critical points, and well, and you have like gradient line that goes like this. So yeah, well, this picture should map to this picture under the flow generated by the gradient lines. Well, you can do that. And you don't need this step, and this, well, yeah, you do basically the same, and you can connect function f lambda and f lambda plus 2 exactly because there is, well, there is a single vector field for them, such that these functions, the derivatives of these functions along this field are positive away from the critical points. Yeah, that's pretty much it about the proof. I'm sorry, we only proved that for this function f, we proved that lambda and lambda plus 2 indeed can be the indices of some extensions. And to prove that there are no other indices, you need Morse-Baranikov complexes. And that's what I'm going to talk about now. I don't have much time, so I will try to be brief. So Morse Baranikov complexes. And from now on, pretty much everything I say is written in the paper by Baranikov. So I will just reproduce it. Okay, so suppose you have a function f in a neighborhood of the unit sphere, and let's note by small f its restriction to the unit sphere. And yeah, let's say that there are no critical points of the function large f at the unit sphere. So the f never vanishes on the unit sphere. And let us pick a metric such that, well, a good metric, such that the ascending and descending manifolds for the function small f on the unit sphere, they all intersect transversely for different critical points. And the Morse-Baranikov complex is the following picture. First, you draw a number of lines, well, n plus 1, n of them. Then for each critical point, I should probably go to some other Blackboard. I will. So yeah, if you have a critical point of the function on the unit sphere, then you put a vertex with coordinates, well, first the Morse index of this point, and the vertical coordinate is the value of the function at this point. And if you have, well, you look at the usually defined differential in the Morse complex. So it's some linear combinations of critical points of index 1 less. Yeah, and this coefficient is just the signed number of gradient lines from, where do they go, from P to Qi. And so, yeah, if differential of your point P is this linear combination, so this is lambda P, this is lambda P minus 1, your points, let us number them in the order of increasing of the value of the function at these points, Qm. Well, there might be some others. This is point P, so you draw edges with labels equal to the coefficient at the corresponding critical point. Of course, if the coefficient is 0, we don't draw any edge, and we don't write a number if it's equal to 1, and so on. So let me illustrate it on this picture. So here, only two critical points. One is the minimum, one is the maximum. And so it's like this. And also on the Morse-Barenkov complex, you indicate where the gradient points. So if gradient of function f at point P points out, then you put an arrow up. If it points in, you put an arrow down. So in this example, here it points out, so the arrow goes up. Here it points in, so the arrow goes down. Now what happens here is that you insert two critical points. And both of the gradients, they point in. So your picture is like this. Well, there are 4 gradient lines. And some of them have negative signs, so I get this, it should be -1, this should be -1. And for the upper picture, the Morse-Barenkov complex looks like this. You put 2 new critical points, and both the gradients point out. And again, you have all the 4 gradient lines. After changing it, what happens is that you change the direction of one arrow, and here you change the direction of this arrow from down to up, here from down to up. And here you change the direction of 1 point from up to down. So from up to down. Okay. Yeah, well, this doesn't change anything. Yeah, that's it. And we see that in our transformations, the Morse-Baranikov complex changes somehow, and in fact, it changes in a very particular way. So if you know some search theory, then you know that any two Morse functions can be connected by a path such that all the functions in this path are either Morse functions or functions having a singularity with, well, such that the matrix of second derivatives is degenerate, but degenerate only in one direction. And so that's what happens if you pass along your path connection to your functions through a function with this simple singularity. Then you add or delete two critical points, and it turns out that you can only add or delete two critical points with the same direction of arrows. And if you like changing your function in such a way that it remains Morse, then you only move the values at the critical points, and these values, they move in the right direction of the arrows. And that's basically it. That's all the possibilities you can have if you do not meet a critical point of the function, like of the whole function, which is defined in the whole ball. And if you pass through such a critical point, as Baranikov proved, you can indeed do it in such a way that just direction of one arrow changes. And it can change. So here we pass through a critical point of index 0, and it changes from up to down. And indeed, for index lambda, we can have on the level lambda a change from up to down. And here in the upper picture, the index of the point we pass through is 2, and we change one. So yeah, the other possibility is that on the level lambda minus 1, we change the arrow from down to up. And that's it. There are no other possibilities to come through a point of index lambda. Yeah, and then by carefully analyzing what can happen in these pictures, and also introducing so-called canonical forms, so like further simplifying these pictures, you get abstractions to the possibility to exchange your function to the unit ball in some way. I mean, because, well, okay, if I have one more minute. Okay, thank you. So you have your function near your unit sphere. You have one critical point. Let's look at the small sphere here, and let's look how the function changes when we go from the smaller sphere to the larger sphere. And yeah, as we know how Morse-Baranikov complex can change by when we go from the small sphere to the larger sphere, we obtain some abstractions to the existence of such a function. And that's how you prove that in this case you have only one Morse index, and in the main result there are indeed no other indices but lambda and lambda plus 2, such that the function f can be extended with these indices. Thank you.
Okay, thank you very much. Some questions, please, from internet first. Some comments. Irina Yurievna, certainly you have to say something, please.
Well, I have actually I have a remark, not a question. Can you hear me?
Yeah.
Well, it's indeed a funny problem which came to my mind once. And what I wanted just to say that first, I spent a lot of time trying to resolve this problem using the Gromov's H principle, the celebrated H principle, but I failed. And then it was my idea that probably one should look at Morse-Baranikov complexes, and I advised to do this to Daniil, and the rest mainly I would like to say that the main job, the whole job was done by Daniil himself, although I was his supervisor. So I like the way he did it. And there is still room for improvement because not all possible subsets of this set of numbers is determined, which can serve as the possible Morse indices of the extension. Thank you.
Okay, thank you very much. Some more questions, some remarks, please.
Do you have examples where this set is bigger than 2 elements?
No, not yet.
Not yet. Okay, thank you.
Yeah, but like if you look at the Morse-Baranikov complexes, then like there are some metamorphoses of them that like allow you to get more than 2 different indices. But unfortunately, these metamorphoses are not, they can be realized geometrically. So, yeah, but I don't know whether it's not possible at all, or I'm just, haven't found yet the right metamorphosis of the Morse-Baranikov complex.
Okay, are there some more questions or remarks? If there are no, let us thank our speaker again. We have some small technical break. Our next speaker is Sergei Agapov from Sobolev Institute of Mathematics and the Novosibirsk State University. He will talk us about the construction of exact solutions in the problem of integrable geodesic flow. Please, you're welcome.
Окей, thank you. Могу я указку сказать?
Да. Все это прекрасно.
Все. Так, а сама указка? Ну ладно. Okay, thanks. Dear colleagues, first of all, let me thank the organizers of this nice conference for possibility to participate and to give a talk here. So I'll be talking about integrable geodesic flows and also magnetic geodesic flows on two-dimensional surfaces. And before going into details and describing the main problem and the main aim of my talk, let me first of all briefly recall you some very basic definitions. So consider a two-dimensional surface M with the Riemannian metric. Given a metric, we may construct a Hamiltonian in such a way, and as well known, the corresponding Hamiltonian system describes the geodesic flow of the given metric. Also, I would like to recall the notion of first integral, namely an arbitrary function which f, which depends on coordinates and momenta, is called the first integral, or equivalently the conservation law of this Hamiltonian system if it conserves along the trajectories, or equivalently the Poisson bracket of f and the Hamiltonian vanishes identically. So of course, one of the key property of such Hamiltonian systems is to be integrable. So as we know, the Arnold-Liouville theorem says us about integrability, namely such Hamiltonian system is called completely integrable if it admits a complete set of first integrals, which are functionally independent almost everywhere. So in this case, Hamiltonian doesn't depend on time explicitly, so it of course conserves. It is the first integral itself. So for complete integrability, we need just one more first integral f. And if the system is completely integrable, then the equations of motion can be integrated in quadratures. So at this moment, we arrive to one of the classical problem of differential geometry. Given a two-dimensional surface, we want to describe all the possible metrics on it with integrable geodesic flows. So in this case, this problem reduces to searching just one more function f, which conserves, and plenty of works is devoted to searching of such function. Many mathematicians investigated this problem in this way. So it seems to be, for me, to be the very natural way to investigate this problem, and I will follow this way as well. And as I shall demonstrate it a little bit later, searching for first integral can be reduced to searching for solutions of certain quasi-linear system of PDEs of such form or maybe such form. It depends on coordinates which you work in. Here is U is a column of the unknown functions U1, UN, which depends on two variables, xt or xy. And matrices A and B depends on the unknown functions U, but do not depend on its derivatives. So we have such quasi-linear system systems of PDEs, and they appears in many areas of mathematical physics, for example, as gas dynamics and many others. And
Excuse me, may I ask
sure.
a question? The surface on which you substituted, or is it just torus or sphere? What about genus?
Actually, one of the part of my talk will be devoted to two-dimensional torus, but at this moment we do not fix the genus. It doesn't matter at this moment.
Do you know any examples of integrable geodesic flows and type genus?
In analytic case, no. There is a theorem by Valery Vasilievich Kozlov, and okay. One of the main aims of my talk will be to describe systems of such a form which appears in the problem of geodesic flows and magnetic geodesic flow. And I also would like to describe some methods which sometimes allow to integrate these systems and construct explicit solutions to the system. Okay, in the overwhelming majority of known integrable cases, if a mechanical system admits first integrals, then these integrals are polynomial in momenta, or maybe functions of such polynomials. So it is very natural to start the investigation telling about polynomial integrals. And the first result I would like to tell you about was obtained by Valery Vasilievich Kozlov in 1995. So if we choose the conformal coordinates, then it states that for any number n, as large as you want, there always exists an analytic function such that its geodesic flow admits an irreducible first integral, which is polynomial in momenta of the given degree n with analytic coefficient, at least in a small neighborhood of a point. So in this sense, the family of integrable cases is pretty rich. And I would like to go into details a little bit and to tell us about the proof. The idea is very natural and quite simple. So if we consider a polynomial first integral of the given degree and write down the conditions on f to be an integral, then we obtain a certain quasi-linear system of PDEs of such a form. Actually, it doesn't matter which exact form it has. But the main idea here is that one may just apply the Cauchy-Kovalevskaya theorem to this system to prove the existence and uniqueness of an analytic solution. So that's the point. And as you can see, this is the existence theorem. And at this moment, a couple of very natural questions appear. And one of the questions is how to construct these solutions explicitly, how to integrate the system. And one more question is the following. What will happen if we try to extend these solutions from a small neighborhood of a point to the whole phase space? Can we manage to do this? And first of all, I would like to answer the second question. It concerns the behavior of the global behavior of solutions to such systems. And the main problem here is that in typical situation, if we, for example, choose an arbitrary matrices A and B, consider a Cauchy problem with certain initial data for the system, then almost always some derivatives at some points go to infinity and the solution goes up. This is a very typical phenomena, and I would like to illustrate this on this simplest case when we have just one quasi-linear equation. This is a very well-known Hopf equation, which also appears in many spheres. So we have this equation. We may consider the Cauchy problem for it, having the initial function, and the general solution can be given by this implicit formula, and it can be shown by the standard method of characteristics that if the initial solution is non-constant, then characteristics, in this case, they are just straight lines, they intersect some point and the solution blows up. It has a very clear physical meaning also, the initial profile, G, and the higher any point is placed, the faster it is, and at a certain moment, the solution blows up. So this is a very typical situation for solutions to such quasi-linear systems. However, sometimes global analytical solution exists, and I will show you a couple of them which relate to geodesic flows. One more obstacle to the global complete integrability was also found by Valerius Ilyich Kozlov in 1979. That is exactly what you were asking about, by the way. If we consider a surface of genus larger than 1, then on the surface there is no Riemannian metric with integrable geodesic flow, at least in the class of analytical functions. So these are certain topological obstacles.
And you said that was analytical.
Yes, of course. If we consider, for example, smooth, but smooth functions, then as far as I know, this is an open problem if this theorem holds true or not. Okay, now let me go to the first question I was asked about certain solutions which are known to exist. So if we consider two-dimensional sphere and two-dimensional torus, then there are many integrable cases. In the case of two-dimensional torus, these cases are rather simple. And the first example, which metric depends only on one variable, then a linear in momenta first integral exists. The second case corresponds to Liouville metrics, when one can separate the variables. In this case, the quadratic integral exists, and equations of motion can be integrated in quadratures in these cases. Okay, on two-sphere, there are also integrable cases, and there exist polynomial integrals of degrees 1, 2, 3, and 4. By the way, quadratic integrals on the two-sphere as well as on the two torus were described by Kolokoltsov in 1982. And what about integrals of degree 3 and 4? For example, if we consider we consider equations of motion of a rigid body with a fixed point, then there exist many famous integrable cases by Euler, Lagrange, Cheplygin, Kovalevsky, etc. So in those cases, there exist polynomial integrals of degree 3 and 4, for example, and by Maupertuis principle, one may modify these examples to obtain integrable cases on the two-dimensional sphere. It was done in works by Bolsonov and Matveyev, and also Kozlov. And there is a conjecture about these examples on two-dimensional sphere and two-dimensional torus. This this is all we know about it. And Kozlov proposed the conjecture that there are no other integrable cases which cannot be reduced to these ones. So this is the conjecture, and it seems to be true for two-dimensional sphere. I'm sorry, it seems to be true for two-dimensional torus, but it is still not proved, even in the simplest case for cubic first integrals, for example. So if we consider a cubic integral on two-dimensional torus, this problem can be reduced to these quasi-linear PDEs, and one have to search for solutions to the system. It doesn't look very complicated, but the only known solutions to the system which can live on the two torus correspond to this case when a linear integral exists, and the cubic integral can be obtained by, for example, multiplying this integral on Hamiltonian, etc. So it's an open problem. There are many results on this direction which were obtained by Kozlov, for example, Denisova, and that's what I'm going to tell you about at the moment. They managed to prove this conjecture for two torus only under certain additional assumptions, either on the metric, as in the second theorem, metric is assumed to be a trigonometric polynomial, or these additional assumptions are on the first integral. So there are certain symmetries, either f is even on momenta, or maybe even or odd in the corresponding momenta. Under these assumptions, they managed to prove then the integral of high degree can be reduced to an integral of degree 1 or 2. Another series of results was obtained in works by Bialy and Mironov. They didn't. They considered the general case, general metric, and the general first integral polynomial in momenta. So they managed to prove that if geodesic flow admits a polynomial integral, then one may introduce globally semi-geodesic coordinates. F can be written in the following form. There are certain coefficients can be normalized in such a way, and this problem reduces to this quasi-linear system with such a matrix A. And one have to search for solutions to this system. Moreover, it turns out that this system has certain beautiful properties. It is semi-Hamiltonian. It means that, first of all, it can be written in the form of conservation laws. And one more property is that in the hyperbolic domain, it admits Riemannian invariance and can be diagonalized. So the now I would like to describe some methods which allows to integrate such systems, and let me start with the classical Hadograph method, which is very well known. So it deals with the quasi-linear system of such a form. We have two unknown functions, f and g, which depend on two variables, x and y, and a ij is just functions of f and g. So the matter is that we just interchange the unknown functions f and g and the independent variables x and y. So we, after making some simple calculations, we obtain such a system of PDEs on unknown functions x and y, which depend on x and g. And in contrast with the initial system, this one is linear, and sometimes it is easier to deal with linear systems. Of course, it can be generalized on the case of when we have more unknown functions. For example, extended Hadograph method deals with such a system. And to apply it, we need to construct an additional flow of such a form. And of course, these two flows must commute. And if they does, then after similar calculations, we may obtain also a linear system on the unknown functions x, y, and t. Okay, and finally, the generalized Khodogrov method, which was proposed by Sergei Petrovich Tsarev in 1985. It deals with so-called semi-Hamiltonian systems. So if it is already written in the form of in the diagonal form in Riemannian invariants, then first of all we have to construct a symmetry of the system, and then given the symmetry, we may construct a solution to initial system of PDEs, just solving the following system of algebraic equations. So the deal is that we, instead of solving these PDEs, we just have to solve these algebraic equations. And of course, sometimes it's not easy. And the only known example when this method works for geodesic flow. I also would like to say that if the semi-Hamiltonian system is written not in the diagonal form, then this method also works, and slightly more complicated formula, but actually it doesn't matter at the moment. So the only known example when this method works for geodesic flow, it was described in the work by Abdikalikov and Mironov in 2019. They managed to construct an example of integrable geodesic flow on two-dimensional surface with a polynomial integral of the fourth degree. So the coefficients of this integral and the metric were found explicitly by this method. Okay. No way, no chance to construct on the torus. They, of course, not periodic coefficients. Just
what surfaces?
no, I guess this is just a plane with maybe.
Oh yeah, it's local.
Yeah, sure. These solutions which are produced by Khodogrov methods are almost always local. Of course, since we have to solve such algebraic equations, we have to inverse functions, just as in the usual Khodogrov we inverse functions.
Can one see that it doesn't reduce to degree 1, for example?
Degree 1, the matter that if linear integral exists, then in some coordinates metric has the following form. It doesn't depend on.
You don't know what is the coordinates are, right? You could change the coordinates. This monster could simplify to something like this.
Yes, theoretically it may be. Sometimes, usually just maybe calculate the Gauss curvature, and if it is not vanishes, it doesn't vanish, then it's okay. But
anything that comes from Newton's theorem, like from metrics of revolution, like that, is it degree 1?
Yes, sure.
So Gauss curvature would vanish then.
Yeah, it's slightly different questions, but of course you're right. That's a right question, but this question, this integral case seems to be non-trivial in that sense.
Yeah, it looks complicated enough, but you know.
Yeah, yes, you are right. Of course. Okay, now let me go to the case of non-polynomial integrals, and the first example I would like to tell you about is the following. These two functions were found in this work, and they these functions commute with respect to the standard Poisson bracket. And as you can see, it depends on the parameter alpha, which is arbitrary. So depending on this parameter, this integral can be polynomial, maybe rational, and even transcendental. And if we talk about geodesic flows, then it is enough to put f. Yes, here f is an arbitrary function of momenta. If we put f in such a way, then we obtain a Hamiltonian which corresponds to a certain Riemannian metric, and its first integral is a rational momenta. So from this moment, I will be talking about rational integrals. And one more example. Excuse me, how much time do I have?
Still something. 10 minutes at least.
Oh, I think then I will skip this example for brevity, since I'll maybe out of time. Okay, so the general result which was obtained by Valery Vasilievich Kozlov in 1914, sorry, in 2014, corresponds to the case of rational integrals. And actually, I started my talk by talking about analogous result by Kozlov concerning polynomial integrals of an arbitrary degree, and this is analogous result for rational integrals of such a form for any numbers, for any degrees of numerator and denominator. We always there exists such function lambda such that its geodesic flow admits such an integral. And also this is the theorem of existence. And in this paper, Kozlov proposed a few questions. One of them was about explicit integration of the corresponding equations and searching for examples of such metrics and first integrals. So in this paper, there were no examples. And this is what we were trying to do in 2020 together with Vlad Shubin. We considered the simplest case when the degrees of numerator and denominator are equal just to 1. And in this case, the question of existence of such integral reduces to this PDEs, system of PDEs. And we managed to integrate the system and to construct a rich family of explicit solutions. And here the slides are just some of these solutions. First example, there are Bessel functions, so non-elementary functions in metric and first integral. The other examples are expressed in terms of elementary functions. These two examples are trigonometric ones, and I also would like to notice that these examples are superintegrable. In these cases also exists a quadratic element of first integral. And one more example when also in elementary functions. So I would like to maybe very briefly give some key ideas of the proof, how I managed to construct this. But no, maybe if there is interesting, I may describe it after my talk. But at this moment, I will skip it, since I want to.
No, at least main result. What is the main result?
Oh, that's not the main result of my talk. It's just one of the results I would like to tell you about. Since I also would like to tell something about magnetic geodetic flows. For them, there are many interesting integrable cases. So the last one thing I would like to tell about rational integrals, that very recently on archive appears the work by Professor Kolodzinski, who managed to construct certain examples of rational integrals, but from a completely different point of view. Okay, now I would like to tell about magnetic geodesic flow. In this case, we consider the Hamiltonian system, but the magnetic Poisson bracket has the following form. So momenta do not commute anymore, and this function just corresponds to the case of magnetic flow. And in this case, the problem is given a surface. We want to find such a pair of magnetic field and metric, Riemannian metric, such that its magnetic geodesic flow is integrable. For brevity, I will describe only two-dimensional torus. So if there is no magnetic field, then, as already told before, these are integrable cases. And if there is a magnetic field, then these two known cases, two integrable cases are known when integrability takes place at all energy levels. In the first case, there is a Euclidean metric and a constant magnetic field, and there exists the first integral of such a form. And the second case, when magnetic field and the metric depends only on one variable, in their case exists a linear momenta first integral. So these are examples of integrability on all energy levels on two-dimensional torus. And yes, I think I'll skip it as well. I also would like to notice that integrability for the standard geodesic flow, it is just equivalent if we consider the integrability on a fixed energy level and on all energy levels due to homogeneity. So different energy levels have the same trajectories up to reparametrization. But it is not true for magnetic geodesic flow because dynamics changes on different energy levels. And the first result, which can describe it in explicit form, was obtained by Evgeny Alexandrovich Taimanov in 2016. He managed to prove that if we suppose that the magnetic geodesic flow on a two-dimensional torus admits a quadratic first integral on at least two different energy levels, then already in some coordinates, metric and magnetic field depends only on one variable, and in this case exists a linear first integral. So in the sense, quadratic integrals on two different energy levels reduce to a linear integrals on all energy levels. And after that, this result was generalized on the case of an arbitrary degree. If we have a cubic integral on two different energy levels, then this the similar result was obtained in the work by Professor Butler and Naqvi. It's his student, she's his student. And recently, we together with Alexander Veluzhenich and later also with Vlad Shubin, we managed to generalize this result on the case of arbitrary degree first integral. And this is written the idea of the proof. Okay, let me go further. And maybe the most interesting point here is to consider an integrability on the two torus on a fixed energy level. This question reduces to such quasi-linear system with such matrices A and B, and this system is also proved to be semi-Hamiltonian. And the main point here is that this system admits a rich family of global analytical solutions which live on the two-dimensional torus. And some of these solutions can be even written down in explicit form, and these solutions can be obtained from the work of these 4 authors. This is the initial system, and this is an explicit solution to the system. As you can see, S and R are elliptic functions, and all this construction is quite complicated, but it is parameterized by a certain number of arbitrary parameters, alpha, beta, gamma, etc. So this is the only explicit solution to the system which is known up to the moment. And also, it turns out that this system has an even richer family of solutions, and that's what we managed to prove in 2017 together with Bialy and Mironov. But we cannot integrate the system and construct the solutions explicitly. So this is the existence theorem in some sense. And if I have some time still, I will give you a sketch of the proof, because in my opinion, it is very interesting. So of course, this system has an obvious solution which corresponds to the Liouville metric and the zero magnetic field, as for the standard geodesic flow. And then what we are doing, we construct a convolution flow of this system of such a form with such matrices A and B. So since this is a convolution flow, it transforms solutions of the initial system into solutions. And we managed to prove that if we consider a Cauchy problem for this evolution equation with the initial data which corresponds to Liouville metric and zero magnetic field, then after transforming this initial data along this flow, we obtain something which is still a solution, but metric is no more Liouville, and moreover magnetic field appears. And this is exactly what is written here. So on the 2 torus, there exist analytic Riemannian metrics with which are arbitrarily close to Liouville metrics, and at the same time they are different from them, and also a non-zero magnetic field, such that the corresponding magnetic geodesic flow admits a quadratic first integral on a fixed energy level. Okay. And, sure. Okay, so 1 minute, right? Okay, fine. The last one result, very briefly, together with my student Alexey Potashnikov, we managed to find the following integral case. So this is still the same system which corresponds to magnetic geodetic flow on the 2 torus, but since it is semi-Hamiltonian, we decided to try to apply the generalized Hadrograph method. So we construct certain symmetries of this system, and this method produces the following. So f and g are 2 unknown functions which satisfy the following 2 equations, and alpha, beta, etc. are just arbitrary parameters here, and the metric has the following form. And in the simplest case, when alpha and beta are equal to 0, we manage to find the explicit solutions, which is written on this slide. So, of course, this is not a 2-dimensional torus, but nevertheless, certain explicit solutions are obtained. Okay, and that was all I would like to tell you about. So, thank you for your attention.
Okay, thank you very much. Some question, please, from internet first. No comments? Maybe there are some questions in this room, please.
Lots of that.
Yeah, many thanks.
Well, I understand that it's quite interesting story which was told by our lecture. And certainly we should say this is quite important for the development of the theory, and the results certainly are very interesting. Okay. Okay, if there are no more questions, let us thank our speaker again. So now we have a coffee break for 20 minutes.
Можно нас включать через 2 минуты. Вот наш микрофончик. Окно лучше закрыть, иначе
Good day.
Yeah, good day. We are ready. Just 1 minute more, please. 2 minutes. Это знак свыше. Начинать. Okay. Let us continue our section. The next speaker today is Dmitry Yuryevich Volkov. He will talk us about Yuri Alexandrovich Volkov and his work on the theory of convex bodies. Please, you're welcome.
Thank you very much. First of all, I am grateful to the organizing committee for the opportunity to participate in the conference. I am very pleased to speak of this conference. Maybe some of the scientists remember Yuri Alexandrovich. My report is devoted to the works of, My report is devoted to the works of Yuri Alexandrovich Volkov. This is his photo. Briefly about the life of Yuri Alexandrovich. Biography is presented on this slide. Yuri Alexandrovich was born in Kazan. In 1947, he entered the Leningrad University. Since then, his whole life has been connected with the university. Yuri Alexandrovich studied on the same course with famous geometer Yuri Grigorievich Reshetnyak. In these years, the famous seminar of Alexander Danilovich Alexandrov, Alexander Danilovich Alexandrov worked at the faculty. These slides show the famous participants of the seminar. From left to right, Yuri Fedorovich Borisov, Alexey Leonidovich Werner, Viktor Abramovich Zalgaller, Evgeny Polikarpovich Senkin, and Alexander Danilovich Alexandrov, and Yusupov, Reshetnyak, and others. We consider Yuri Alexandrovich began to work of the Alexandrov seminar from the second year. Professor Zalgaller spoke about Yuri Alexandrovich
in a famous book about Alexander Danilovich. Consider this site. Yuri Alexandrovich wrote, Viktor Abramovich was a modest and reserved man. He taught a course on geometry to students of mathematics for 25 years. He prepared his course perfectly, but assumed that students read the text. Therefore, some of his remarks were not understood by them. Students were afraid of him. But the postgraduate students adored him. He helped them skillfully to develop their knowledge, talking to them for hours evenings in this hall. Viktor Abramovich said the famous problem Yuri Alexandrovich studied was two problems. He proved the existence of convex polyhedron with a given development, and he also solved a famous Weil-Conforson problem, obtaining an estimate of the deformation of closed convex surface in terms of deformations of its metric. Consider this problem. Briefly, I talk about history Weil problem. This is a famous scientist, Hermann Weil. He considered this is a Semyon Nathanovich Bernstein. This is a Hans Levy. What is the Weil problem? We consider isometric immersion. I'm sorry. The problem, the Weil problem, is a problem of isometric immersion of the Riemann space of positive curvature with a homomorphic to a sphere into three-dimensional space. The first complete solution of the problem given by Levy for analytic metrics. He considered the famous Darboux equations. These equations is type of Monge-Ampère equations, and Levy considered this problem with a problem of partial differential equations. New method consider Alexander Danilovich Alexandrov. He gave a new simple solution. The solution this problem. He proved that a general convex metric given on the sphere could be realized in general in the form of general convex surface. This solution is first of all, this solution Alexandrov proved that a polyhedral convex metric given on sphere could be realized by a closed convex polyhedron. This is a basic theorem for my talk. This is a slide. We see the famous scientist Alexei Vasilyevich Pogorelov. He studied of regularity of the solutions of the Weil problem. This is Louis Nirenberg. He considered this problem in analytical sense. consider the theorem of Alexander Danilowitz. We see the polyhedron, this is a cube, and this is unfolding this cube, development or net this cube. We consider unfolding, this is a basic step, and the final step, this is a cube. Alexandrov said, что any metric positive curvature which is given on the sphere realizable by a closed convex polytope. This is an unusual theorem. Consider example of non-trivial development. Trivial development, this type. We consider this is the age of this polyhedra. In this development, we don't see the age of this polyhedra, and theorem of Alexander Danilowitz is not easy theorem. The development is a very delicate object. Many proofs of these theorems are available. Alexander Danilowitz found two proofs. One proves topological proofs based on mapping lemma, and second is a method of parametric extension, Bernstein method. In 1941, Lusternik proposed the approximation polyhedral metric by analytical metrics, and Yuri Alexandrovich Volkov consider the variational approach this theorem. On Friday, Professor Viktor Alexeyevich Alexandrov will talk about interesting problems concern this theorem. He will consider the affine equivalence of natural unfolding. We consider the variational approach of this theorem. I'm sorry. Remarks about this theorem. Alexander Danilowitz, in the famous book, makes such a remark. This remark you can see on the slide. The age of convex polyhedron must be short arcs joining the vertices of the development. We consider on this slide, we consider this is a true vertices. This is a false vertices. Alexander Danilowitz said that moreover, the planar angles at one vertex must satisfy the inequalities asserting that each of the angles is less than equal to the sum of the others. If one knows how to draw short arcs in a development, an explicit method for this can be indicated. Then infinitely many cases occur from which we must choose the one that corresponds to the structure of the polyhedron. Consequently, it is possible in principle to effectively solve the problem of constructing a polyhedron by gluing. And we see red sentence. However, in my opinion, effectiveness is of no interest. More important in the fact that because of uniqueness, the polyhedron is obtained naturally in the required form from a gluing. Very interesting problem. What is the algorithm of Alexander Danilovich construct the shortest path? Unfortunately, we don't know this algorithm, and only in computer graphics, researchers studied the algorithm of shortest path. Maybe Alexander Danilovich knew this algorithm in 50 years. Consider the variational problem of this theorem. What is the variational problem? This slide, we see the basic of this method. Alexander Danilovich wrote that it's a very interesting method by in famous book Convex Polyhedra. Alexander Danilovich not studied this method. Only one theorem, theorem Minkowski, is variational method. We consider the Blaschke-Cohn-Vossen method in Weyl problem. Blaschke-Gerglotz gave variational approach. We see the this method. The basic, this method is suffice to extend it inside the sphere in the such way that the Riemann curvature tensor thus obtained vanishes. But unfortunately, Euclidean metric, the integral can reach its maximum, not its minimum value. And now, Weyl problem is not solved with variational method. Consider that Alexander Danilovich gives the problem to the Yuri Alexandrovich to find a variational proof of theorem of convex polyhedron. The main idea of the proof, Yuri Alexandrovich. First step. This step is transformation of original development. Yuri Alexandrovich opened the new type of development. Now, in computer geometry, is called of source unfolding. We can see this unfolding in this slide. On the right, we consider point on this face of hoop, and we consider cut losses. This maps is our point of cut losses. What is this set? This set, every point of this set, we have two and other shortest path basic in this point and end point of this set. This is development. This development is non-overlapping. Alexander Danilович Alexandrov consider other development. Alexandrov development are called start development. Nice. First step, we consider this development. Second step is basic for the method of Yuri Alexandrovich. He wrote, it is clear that any convex polyhedron can be represented as a union of pyramids with a common apex at one of the vertices of the polyhedron. This union is not polytope polyhedron in Euclidean space. This is a union is not in space. What is this? This is describe of this method in theory. The basic step is this step. We consider the angles of the each internal edge this pyramid, and that is angle is even on h exceeds 2p, then this h can be shortened, obtaining a net of the same form. This is based on the fact that shortening one h can only increase the angles at all the other h, which will thus not go below 2 pi either. One naturally expects that the net which shortest total internal h length will have all angles equal to 2 pi and will thus assemble into the Dirac polyhedron. Yuri Alexandrovich considered and proved this theorem of existing convex polytope with prescribed development. This theorem is a theorem of the PhD dissertations. Yuri Alexandrovich here. In Yuri Alexandrovich I'm sorry, PhD thesis in 1945. The time of the talk is a rigid object. I don't a lot of time for descriptions of other works of Yuri Alexandrovich. Consider consider only Confucian problem. This is we see the famous geometer Confucian. What is the problem? I have not the time, and I can talk very short. Given two close convex polyhedra, and consider that distance between their vertices, and consider the distances in space of these vertices. We must estimate this type. This is a distance in space. This is a distances is inner metric, and we consider continuous function with this sense. He considers the theorem Yuri Alexandrovich Volkov. He proved two close convex surface special distance was obtained of the form the space distance equal this constant where alpha is absolute constant. The largest possible value of alpha is not known, but can't exceed this fraction. This is пример этого. Sorry. This is example for this sense. Now I conclude my talk. The basic article, the PhD dissertation, Yuri Alexandrovich, was printed in this journal, and we now we can read the full we can read as full proof of theorem Alexander Nilich's theorem of variational method. Thank you very much for attention.
Okay, thank you very much. Some question, please. Some remarks, some suggestion from internet, please. Or maybe somebody from this room. If there are no more questions, let us thank our speaker again. Now we have a small break up to 5:30.
Okay. А мы сейчас свою на это место поставим. 15 минут достаточный срок, чтобы... Ага.
Так, ну будем по расписанию, раньше не будем.
Конечно.
Александр Андреевич, меня слышно? Все понятно, хорошо.
Включен.
Да, все слышно, все хорошо.
Замечательно.
Ну, я отключусь, требуется.
Мгм.
Так, еще 3 минуты. Что у нас сейчас? Что-то я не вижу их. Ага. Все еще 3 минуты, кажется. Да.
Все хорошо, видно, слышно?
Да. Ну, самое надо покрупнее это. Надо вот сюда ткнуть и как-то вот сюда ткнуть.
Не можно просто на слайд кликнуть 2 раза.
Вот так? Ага.
Okay, I think it's good time to continue our session. Our next speaker today, there are 2 speakers indeed, Yuri Nikonorov and Yulia Nikonorova. They will talk us about one property of a planar curve whose convex hull cover a given convex figure. Please, you are very welcome.
Thank you for the introduction. Many thanks for organizing committee for the invitation and for the opportunity to give this talk. Really, now we have only one speaker, it's me, Yuri. And this is a short plan of my talk. Now we can relax because we will discuss one problem on Euclidean plane only. And this talk is based on the result obtained in our recent paper. This paper is just published online, Elementary Mathematics, and the title is the same, almost the same. One property of planar curve whose convex hull cover a given convex figure. Yes, you also can find similar paper in arXiv. And this paper is devoted to the proof of the following conjecture by Arseny Akopyan and Vladislav Vysotsky. This is the conjecture. Let gamma be a planar curve such that its convex hull cover a convex figure K. Then length of gamma is greater or equal to perimeter of K minus diameter of K. In fact, it's very simple setup. It's easy to check very usual curves and figures, but in fact, the problem is not so easy. I try to explain the problem. I'm trying to explain some difficulties in the proof. This conjecture was posed in the following paper by Akopyan and Vysotsky on the length of curves passing through boundary points of planar convex shape. It was published 4 years ago in American Mathematical Monthly. And it should be noted that the serious partial result was obtained in the same paper by Akopyan and Vysotsky. They proved the conjecture in the case when gamma is passing through all extreme points of figure K, of convex figure K. Okay. Now, a little history. After some computer experiments and after proving in some very special cases, not so special, we believed that the above conjecture is true and found some strategy to obtain the proof. The main idea to prove this conjecture was the following. Let us fix a planar convex figure K and let us find so-called the shortest curve gamma 0 with the property that its convex hull cover K. If for this gamma 0 we have the equality that length of gamma 0 is greater or equal to perimeter of K minus diameter of K, then of course conjecture is true in general, because gamma 0 is shortest from among all curves with this property. Okay, the idea is reasonable from the first sight and from the second also, but on the other hand, it's not obvious what is the shortest curve in the general case. In fact, the curve gamma 0 may not be unique, for example. For instance, if K is a equilateral triangle, then the union of any two of its sides is such a curve. Hence, we have 3 shortest curves in this simple case. Moreover, the curve gamma 0 could be non-convex. Let us consider the following example. Let's K be the parallelogram ABCD on the Euclidean plane, which we identify with R2, with the vertex A 0, 0, B 1, 1, C T plus 1, 1, and D T 0, where T is greater or equal to 1. It's easy to see that the broken line A, B, C, E, where E is point with the coordinates T plus 1 and 0, this broken line, is one of the shortest convex curves whose convex hull cover K, and its length is 1 plus square root of 2 plus T. On the other hand, the length of broken line A, B, D, C, which convex hull is also K, is equal to this number, and it's easy to check that this number is less than the length of the first broken line for sufficiently large t. For example, for t which is greater than 1.6. This means that the shortest curve gamma 0 in our notation could not be convex in the case of such parallelogram. Therefore, we have additional problem. Now, I should refine some definition and recall some useful result which could be used as a tools in the proof of this conjecture. All this notion are well known and all are quite standard, but of course I should say something. For example, Euclidean plane we identify with R2 with the standard distance, Euclidean distance. For every point BC in R2, this symbol denotes the line segments between these points. A convex planar figure is any compact convex subset of R2. And we shall denote by pair K and BDK, respectively, the perimeter and the boundary of convex figure K. Note that perimeter of any line segment, it is degenerate convex figure, is assumed to be equal to its double length. It's reasonable from various points of view. For example, in such definition, we have the continuity of perimeter for degenerate and non-degenerate convex figure. Note also that the diameter of K, of convex figure K, coincide with the maximal distance between two parallel support lines of K. And recall that extreme point of K is a point in K which does not lie in any open line segment joining two points of K. The set of extreme points of K will be denoted by the symbol xk. It's well known that xk is closed and K is the convex hull of this set for any convex figure K in Euclidean plane. Yes. What is a planar curve? We refine this definition. Planar curve gamma is the image with continuous mapping phi from any segments of R to R2. From now on, we will call planar curve simply curves for brevity, since no other curve are considered in this talk. As usually, the length of gamma is defined as supremum of broken inscribed line. This is very standard definition. And one more standard definition, a curve gamma is called rectifiable if its length is less than infinity. One more definition, we call a curve gamma in Euclidean plane convex or closed convex if it is a closed connected subset of the boundary, respectively the Kuhl boundary, of the convex hull of gamma. Okay, it's more or less standard. We first recall some important properties of curves and convex figures. Now we should recall some results that are tools for studying of our problem. The sequence of curve gamma y converge uniformly to a curve gamma is the curve gamma y admits parameterizations with the same domains that uniformly converge to some parameterization of gamma. We will need the following results. Proposition 1, Arcellas Colli theorem for curves. Given convex metric space, any sequence of curves which have uniformly bounded lengths has uniformly convergent subsegments. It's very important in our construction. And another important thing that's also very well known, the lower semi-continuity of lengths, is the following proposition 2. Given a sequence of rectifiable curves gamma y, which converge pointwise to gamma with respect to parameterization with the same domain, then we have an equality. Lower limit of length of gamma y is greater or equal to length of limit curve gamma. Okay. And the following well-known property, monotonicity of perimeter of convex figure, proposition 3. If convex figure K1 and K2 in Euclidean plane are such that K1 is subset of K2, then perimeter of K1 is less or equal to perimeter K2. And the equality holds if and only if K1 is coincide with K2. And another very well-known result, it could be proved using the Crofton formula, for example. Proposition 4. Let phi maps from segment CD to R2, sorry, be a parametric continuous curve with phi of C is phi of D, then the length of curve gamma is greater or equal to perimeter of convex hull of gamma. Moreover, the equality holds if and only if gamma is closed convex curve. All these results are very well known, and I only recall it. And what is about conjecture? What is about proof? In fact, we have only these 4 propositions in order to construct some proof, because the problem is very simple in its setup. We have no serious tool to do something. Therefore, we should construct something from that 4 proposition. And the first result is more or less standard, proposition 5. For a given convex figure K on Euclidean plane, there is a curve gamma 0 of minimal length among all curves gamma satisfying the condition K. The condition K is a subset of convex hull of gamma. The proof is quite standard. There are many such results in some extremal problems on the Euclidean plane, and it's quite or less standard. But of course,
sorry,
yeah?
sorry. The curve in proposition 5 is unique.
No,
Is a curve, but it is unique.
It is some curve, but it should not be unique. It could be, yes. I recall that in the if K is triangle, is a regular triangle, then union of any 2 sides of this triangle.
Yes, yes, I know, but in your example, the curve is not be convex. But
it should be. It should be not. It should be. It should not be convex. Yeah, it could be non-convex, really. But it is a problem. It's really a problem because the next step to obtain some good property of this possibly non-convex curve to get the complete solution of the conjecture. And the following open problem is quite natural. Problem 1. Give a comprehensive description of the class of planar curve gamma with the following property. There is a compact convex figure K on Euclidean plane such that gamma is the shortest curve among all curves whose convex hulls cover K. Really, I don't know what is the right answer to this problem. It could be very complicated problem, in fact, but interesting. we know that the results of gamma 0 should not be convex, but in any case, this curve have very special property, very special property. And the final part of the proof of the conjecture line is scrupulous and detailed analysis of the properties of this shortest curve gamma 0 and its connection with the extreme points, with the set of extreme points of a convex figure K. Unfortunately, the complete proof is quite long, and I should say only this. Using several quite technical results, we prove the following corollary. If a curve gamma has a shortest length among all curves whose convex halves cover a given compact convex figure K, then the following inequality holds. The equality which we want to prove. Length of gamma plus diameter of K is greater or equal to perimeter. Moreover, the equality in this inequality is fulfilled if and only if gamma is convex, boundary of K is union of gamma and the line segment AB, and the diameter of K is the distance between A and B, where A and B are the endpoints on the curve gamma. Really, this is almost proof of general conjecture, but to obtain these results not so easy really. It's several, I think, six page in the journal formats. Okay, but in any case, this result implies the following main theorem for again almost the same statement. For a given convex figure K and for any planar curve gamma with the property K is subset of convex half of gamma, the inequality length gamma is greater or equal to perimeter K minus diameter K holds. Moreover, this inequality becomes an equality if only if gamma is convex curve, boundary of K is the union of gamma and line segment AB, and diameter K is exactly distance between A and B, where A and B are the endpoints of gamma. Yes, this is final result. And from this result, we obtained very well-known results. Length gamma is greater or equal half of perimeter K. Because perimeter of K is greater or equal twice diameter K, it's obviously, I think. And in fact, we can consider another picture, another figure 2, example 2. Here we have two examples of gamma, this short gamma and this long gamma. In fact, union of this gamma is ellipses. And suppose that the boundary of K is a convex figure K is the union of the line segment AB and a convex curve gamma with endpoint A and B, either this or this one. Then K is a subset of convex half of gamma. It's obvious in both cases. And length of gamma is a perimeter of K, minus distance between A and B. Yes. Moreover, this length is perimeter of K minus diameter of K, if and only if this diameter is equal to distance between A and B. Hence, for this gamma, we have this equality, but for this gamma, we have not. This is another example. I think this picture is more or less helpful to understand the problem. And moreover, the problem of equality in this inequality. It's not so easy. But in fact, the proof of theory, when we have corollary for shortest gamma, it's very easy because it's one-line proof. Really, we know that length gamma is greater or equal to length gamma 0, and we prove the inequality. And in case of inequality, we can, without loss of generality, think that gamma is the same as gamma 0, and hence we have a result which we want to get. This is a plan of the proof. And of course, I recall that the main problem is in the proof result for shortest gamma 0. Hence, not hence, but another problem which is interesting in this situation, in this setup, is problem 2. Is it possible to get a natural version of the above theorem for the case of special but not planar curves? We see that we have with 3 so-called one-dimensional thing: length of gamma, diameter of k, and perimeter of k. If we have, say, 3-dimensional case, then we should compare with some also one-dimensional thing. It could be some composition of Fermat's integral, I don't know, root of third degree from volume, and so on and so on and so on. We can construct many suitable for conjecture functionals, but I don't know what is the correct correct statement for corresponding conjecture. But I'm sure that the corresponding results should exist. And of course, a statement of the conjecture should be appeared somewhere, somehow. Okay, that's all I want to discuss. Discuss. And thank you for your time and attention.
Okay, thank you very much. Are there some questions? Please, from internet first.
But it was some article of Victor Abramovich Zalgarin about convents full of the special curves.
Possibly, really, I don't have a search.
I don't know, but maybe it is connected with this thing.
Okay, why not? If you if you know such result, it would be interesting.
You look through this article. Maybe it helps you.
Thank you, thank you. I'll try to find something.
May I ask a question?
Yeah, please.
I thought about you consider a non-closed curve, but what will be if your curve contains several components? It may consist of several points, and in this case, maybe the length will be 0. Maybe example, what if you take your picture with ellipse cut by
just
and maybe instead of half of this ellipse, we will take polygonal curve.
Maybe.
Consider only vertices of this polygon.
I see.
What in this case, probably length will be 0, but I mean the curve will be several points.
Yeah, I see. But in general, we can consider some set of points as a curve, really, with many components. In this case, it's we should clarify what was the setup really, to be precise, I think. The
Yes,
two
maybe-
components.
Maybe when two components, maybe this is
Maybe.
more or less. Thank you.
Thank you also.
And,
More questions, please.
I have a question. Yuri,
Yuri.
Is it possible to consider this tasks for two-dimensional sphere?
Yes, of course, why not? Any two-dimensional Riemannian manifold not only remain.
Okay.
Yes.
Please more. Some more questions.
Yeah.
Yes, I have a question. So I guess there would be another version of the 3D question where you would be trying to cover a convex body with the convex hull of a disk and trying to minimize its area.
Maybe I don't know really. Thank you. It could be discussed. I don't know really. I don't know what is the right answer for the setup of conjecture, even not for the proof.
No, for the
The conjecture might be that it's at least the perimeter minus the largest cross-sectional area.
Okay. Maybe I don't know really. Thank you.
Just the disk wouldn't work. You can make a tiny disk which looks more like a curve and wrap around anything you like. So the area is not a good invariant. The area of a disk that wraps around. It's one-dimensional.
Yeah, something one-dimensional. I don't know. Yes.
Okay, more questions, please. Yuri, I'm very glad to see you and also to hear you. As usual, you try to solve a very elementary problem which has no elementary solution. Yeah, as usual, very successful.
Thank you.
Okay, so more questions, maybe somebody in this room. If there are no more questions, thanks a lot again for very, very beautiful talk. Let us thank our speaker. Okay, so our section is over today. Thank you very much for all participants.
As usual, we offer everyone the opportunity to gather in breakout rooms of Zoom, and we specifically invite the two speakers to enter breakout rooms 1 and 2, respectively, just for a couple of minutes to see if anyone wants to maybe to discuss your talks in more detail. If there are no, okay. So we will leave this equipment on for some time, at least for 15 minutes. So you're welcome to use this Zoom channel further.
Okay. So some discussion probably we can do also in Russian. Юра, чем еще занимаешься в данный момент? Какими проблемами?
Можно пойти действительно в breakout room.
А что он сделал, чтобы пойти в этот рум?
А я даже не знаю. Ну давай.
Тут он есть физический здесь, а в Zoom это...
Какой номер?
Сейчас, в каком порядке? Ну, кто первым выступал, тот, кто предпоследний в breakout 1, а кто последний в breakout 2. А вот тут есть такая кнопочка сессионный зал.
Еще? Что нажать?
Если ее нажать...
Войти в зал 2, короче, да?
Да, а зал 2 у нас на двери написано, вот там, breakout 2.
Окей, я пошел в зал 2. Спасибо.
Хорошо. Это смотрю, как она работает. У нас на брейкаутах. Так, а нам нужно... Что я зря это сделал, да? Надо же его совсем было заткнуть.
Да.
Как остановить?
Да.